still shows.
It's what?
It's still.
Yeah. Yeah. Yeah.
This one?
Oh,
Just
yeah,
some.
it looks right.
But it's still here.
Where's the janitor there? Oh, what happens if you move it from there? Oh. Oh, interesting. So you had the... Take a look at the display configuration and see that it's not mirror, because I think it's just mirroring it. And tell if it's two separate ones. So like look at the Mac display settings.
Okay, should I unplug first?
Yeah, probably. Find where you control the two desktops. More like, yeah. I think it's just showing the same thing on both of them instead of giving you two different displays.
Advanced.
Plug in the other one.
Plug it in.
Yeah, so we'll see. So it should show you two of them, right? Now just tell it. Yeah, so tell it not to. Yeah, not exactly. So now this is gonna be blankish. Yeah.
Oh shoot.
Hey.
Challenge.
This is blank.
Yes, okay.
We're just testing out.
Okay, thank you.
Okay. Yeah.
Perfect. Good.
Okay.
Awesome.
Yeah, we start. So this is the figures, and we showed this one, and so 5 minutes left, and 3, 1, and
No, keep going. Alright.
so I did so please check, and there's clock.
I think there's one rule. No.
さっきの PC は多分映ってたから
借りたのかな、PC。
大丈夫ってことでしょう。なんかダメだった場合はっていう感じで、そうですね。ラベルファイル吉田さん私は
カンニング。
これ
今日この本を入手しています。
それカウントね。書いてるのがこれチャレンジがラウンドワンタイムカードで何人ぐらいいるかを大体始まってしばらくしたらカウントして、このセッションには何人いたかなっていうのが分かるっていうのが一つ。
紙が来て紙が間違ってる。
紙が間違ってる。
紙が間違ってる。
さっき三谷
さんが私間違い。
大体だから。 はそこで終わってもしも
対比が後ろの方からカウントして
前の方にそれが来て何かあったらでしょうそうですね。あとは後ろに眠なければじっと見てる。
あと質問用とかマイク
ああそうね、ヘアマイクはあそこにないかな。
テステステステステステステステステステステス
Hello everyone, thank you for coming to this session, challenge along long-term kernel maintenance. Please welcome Sasha Levin.
Hey folks, thanks for coming first thing in the morning. Apologies in advance, I woke up at 2 a.m. today. The jet lag is real. And I'll start with a little bit of background about the kernel's stable and LTS story. So the kernel about 20 years ago declared that every release that Linux does is stable. That means that we see a two-week merge window, and then we see about 7 to 8 weeks of release candidates where we try to fix all the issues introduced by the merge window. What does it mean to be stable? It means that after Linux cuts its release, we're taking that kernel and we maintain it until the next release is out. So for about 10 months, we take all the bug fixes that go into the next release, and we put them into the older one, and we're hoping it's something that helps users gain confidence in upgrading to that previously released kernel version. Now, an LTS is a bit different. With LTS, we take usually the last release of the year, we deem it as LTS, and at that point, we do the same process of backporting bug fixes from Linus's tree back onto this LTS kernel. And we do this over a period of 2 to about 6 years. Depends on how much interest there is in that specific kernel. Sometimes it's 2, sometimes it's 4, sometimes it's 6. Depends on the community and its interests. Why are we doing LTS, right? It's not obvious because we just said that every release Linux does is stable, right? The single most important thing to the kernel community is its users. It goes above everything. No new shiny features, no new shiny device support. Really the only thing the kernel community cares about is that users have a great experience using the kernel. And LTS trees or LTS kernels are really this admission that the process we have with upstream is not perfect. We still have bugs sneaking in, we still have issues going into the upstream tree, and some users find it difficult to use the upstream tree. And so to accommodate for those users, we take this project, which is called the LTS trees, where we try and make a more stable kernel, and we pay the price of doing that whole work of backporting, and those users who do not see new features come up until they update to the next LTS tree. Really, what we want to get to the point is that users are happy using this kernel, that they're confident to upgrade from one version to another. They're not afraid of being stuck on this ancient kernel just because something might break. We want the kernel that those users use to have all the fixes that landed upstream. There's literally thousands of fixes landing every release cycle. And we want those fixes to get to users' kernels as soon as we could possibly land them there. And we also want those users to not just to regress when they're upgrading, but also to feel confident to upgrade to every single release that we do. So we release about once or twice a week. There's a new LTS release, and we really encourage all users to pick up that release, run it through their tests, run it through their qualification environment, and then roll that kernel out to the production environment. Why is doing LTS hard, right? The kernel is fairly unique. It's the single biggest open source project in the world. We see over 10,000 new patches in a period of 10 weeks. Linus, in his keynote this morning, mentioned that 6.7 was the biggest release he ever saw commit-wise. And that means that the LTS folks have that many more commits to review so they could ship them to their users. Even though the kernel is over 30 years old, the kernel is still fast evolving. The systems and the architecture within the kernel are changing rapidly. We see introduction of new features, new ways of doing things, which also complicates backports. And I'll talk about all of it in the next couple of slides. We also have fairly limited resources doing this work. Many of us are working on the kernel for their companies individually and so on. Very few of us are paid or encouraged to work for the good of the community. And so we're trying to make a lot of this effort work with a very limited set of resources and people who do this work. And as far as testing goes, it's improving. In the past couple of years, we've seen tremendous improvement in how we test and release kernels. Up to 5 years ago, it was not the best shape. And even now, it still could use some more love and attention, and we're always trying to improve that process. So let's go over the issues I've talked about in the previous slide in depth a little bit. The first one is those easy conflicts we all saw. So many of us tried to take a patch from upstream, put it on some older kernels, and we might have saw some conflicts here and there, probably simple stuff. There are context issues, maybe some spelling changes somewhere that we need to take account of. And those changes seem to be simple, right? We could say it's fairly easy to take a bunch of these commits and kind of backport them to old trees. The tricky part is that this doesn't work at scale. There's only a few of us who can do this manually. And if we see 10,000 commits every release cycle, and let's say only a few thousands of them make it into the stable trees, and let's say only 10% of them have conflicts, it means we have to resolve in the hundreds of conflicts for every single LTS tree that we have. Time-wise, this is not something sustainable. We simply can't do this work. There's only so many hours in a day. It's also the case that sometimes we look at something and when we think, well, this looks like a very trivial conflict and I'll just fix this up and I'll ship it. No one knows what's happening in the kernel. And sometimes things that seem like a very easy trivial conflict are really not. Sometimes we miss context. Sometimes we're not familiar enough with the subsystem. And it's really easy to mess up something that looks like an easy conflict and break user systems. And we definitely don't want to do that. It's also the case that the older kernel trees get. So if you look at kernel trees that are 5, 6, 7 years old, there are drastically more trivial, simple conflicts that happened as we backport patches to them, just because of how much they diverged from upstream. This divergence cost us from having like very simple cherry picks that just work into having to resolve tens or hundreds of conflicts every time we try backport a batch of patches back to LTS trees. This is an interesting one. So the kernel is about 32 years old, and we still see major fundamental changes in the kernels. In the past year or two, we saw the introduction of folios, which is a new way to manage sets of memory pages. We saw major refactoring in the block layer, which deals with decades of technical debt. We saw the introduction of Xarray, which is there to improve performance and scalability, which are wonderful features to have upstream. It's great to see how the upstream kernel can improve so drastically, even though the project is 30 years old. The concern for the LTS trees here is that every time this new feature is introduced, we diverge from upstream in the older LTS trees. So for example, in the 5.15 LTS tree, it will not have support for folios. It will not have support for Xarray, right? And what this means is that we now have this permanent divergence between two trees. And it causes two big issues. One is that further fixes that end upstream, for example, a fix in the memory management system that touches something that works with folios, is now not easy to backport to an older LTS tree. So any new fixes that touch those features will not land in an LTS tree. It also means that sometimes we have issues in an older LTS tree, and those issues are inadvertently fixed by this change. So for example, a bug that was buried in the memory management code, and then the introduction of folios kind of solved it. And we say it a lot, that big refactoring brings new bugs, but it also fixes many old bugs just because it's a new code base. And so what this means is that if you have code that's broken in 5.15 or an older LTS tree, it will just not get fixed because upstream has moved away from using that code whatsoever. So you're forever stuck with having those bugs. I've previously talked about users, and this is kind of an umbrella for what I'll talk about next, is that we're doing this to provide our users infrastructure, which is critical for their uses, whether it's running workloads, running your media player, your cars, and whatnot. The big thing we care about is users, and what we're trying to do is find a way to balance our limited set of resources with trying to support as many users as we can who use the kernel. And what we see is that with newer LTS trees, we have many users, right? Because users upgrade and they adapt new trees, and they end up being mostly on the last like release or 2 or 3. And then the number of users tapers off rapidly as we get to old releases. So currently our oldest one is 4.14, and there's really just a handful of users who still care about it, and I can't wait to get rid of that release. Having said that, it's not the case that we don't care about the users who are on 4.14, we care about them deeply. It's just that when we look at what we can do to support them, our options are fairly limited. The first one is kind of the priorities of what maintainers and what patch authors see as important to them. We often see complex fixes that we want to backport to old trees. And we try them ourselves and we fail miserably. And then we try to find expertise in the field. We try to find people who, whether it's the author of the patch or whether it's the maintainer of the subsystem, to help us and try and both backport the patch and show us ways to test that backport. Which is a problem because, as Linus has mentioned in his keynote, maintainers are already overloaded and overburdened. And maintainers will respond favorably when we ask them to do this work for a kernel that has many users. So the recent LTS kernel trees will probably get help to get it done. So if I were to backport something to 6.6 from 6.7, maintainers would try and help us there because they know that doing this backport will benefit a huge amount of users. However, if I were to ask them to backport a fix from 6.7 to 4.14, and that fix isn't trivial, you'll get queued in there, very long queue, and it's very likely that they will never get to it because to them, they want to have the biggest impact they can have with their time. And when both developers and maintainers look at what they can do in the kernel world, really the best use of their time is doing development on the upstream tree. So fixing issues in Linus's tree, developing new features, improving systems, any work they can do on the upstream tree, it's probably the best way to send the resources to. After they've done this work, if we try and get from the development tree, which is Linus's tree, to the tree that users actually use, which is one of the LTS trees, then those developers also see the value there. They recognize that creating a fix in the vacuum is not enough. So if a fix only landed in Linus's tree but didn't actually reach the users who need that fix, then we didn't really fix the issue, right? The fix is only still theoretical at that point. And so developers do appreciate that, and they do help us with doing these backports to recent kernel trees. What we've seen really going backwards is that the older the tree gets, the less maintainers care about it, both because of the decrease in user count, but also because the delta between the old kernel trees and upstream has grown so much that doing this backport is very difficult. And I think those of us who try doing it occasionally, backporting a kernel patch from one version to the version prior is fairly easy. There's usually not a good chunk of changes there. And usually we see small context changes and it's doable. If we're trying to do a backport to a kernel that's 5 years old, we have seen fundamental changes in the kernel. Some patches become nearly impossible to backport. And developers also know that, and they sometimes might not even try and just ask users to upgrade to the latest tree. The kernel, just like any other project, has been around for a while. And just like any other project, the kernel community is composed of people. And while the kernel tree has stayed with us for 30-something years, some folks have done other things. Some folks have started working, for example, on a particular file system, and then they may have moved on to working on a different file system. They may have moved to work on a different subsystem altogether. Maybe they're moved from file systems to memory management, or maybe they moved to work on something else, which is not the kernel. Maybe they're retired, maybe they're working on Kubernetes, and now it's really hard to get to those developers. And so we see within the kernel trees that we have subsystems and code chunks within the tree that are barely maintained. And when we see issues in those areas of the kernel, we find it very difficult to find the required expertise, both to create patches for those issues, but also to backport them. because by the time we found someone who knows enough about the upstream code to help us, no one really knows how the code looks like in the kernel that's 5 or 10 years old. And it's very hard to find folks who would spend the time and effort to help an orphaned subsystem or a completely deprecated subsystem to go backwards. An example here would be stuff like the Ethereum deprecation, right? We just decided to kill it upstream because there's no expertise to maintain it. There's no machines to maintain it. And so if you're still using that on your older kernel trees, then you really have to upgrade your tree. You really have to move to something that's not Ethereum, I'd say. Another issue is testing, which I mentioned in the past. The kernel at this point has a good set of synthetic tests. We have many tests that go all the way from unit tests to like small functional testing. We have multiple test suites that run and give us results, and they find real bugs. It's something that we didn't have 5 or 10 years ago, and this effort is growing very quickly. Things like kernel CI, things like the zero-day bot are really valuable in this effort. It's wonderful to see so many tests being run every time I push a commit to the stable queue, for example. And it's really great it's a great way for us to gain confidence in the kernel before we release it. What is very difficult for us to get is real-world testing, right? The things we do in practice in our companies, in our home, to run our workloads or products is very different from synthetic tests. Like Unix Bench doesn't represent any real workload. It's great at finding regressions in the scheduler. It's not great at catching issues that will mess up your production systems. And we found it very hard to get feedback from real users on whether we're breaking their kernel or not. No one really wants to throw a half-baked kernel into their production environment just to give us feedback. And so what it means is that we don't have great confidence before we release a kernel unless we get those signals. We don't know what each and every one of you run or use the kernel for, right? Some of it is cars, some of it is spaceships, and some of it is just media servers in your home. And we really can't test for all those scenarios. We really don't know what people do with the kernel. And unless we hear back from folks, we can't help there. We also see a case that people kind of hope that someone else will come and fix the problem for them or find the problem for them even, right? Linux does 7 or 8 release candidates, and there is definite participation in those, but most folks basically just wait until the kernel is released, and then they kind of start testing it because they think at that point the kernel is in a good shape. But if you haven't tested that during those release candidate cycles, then it's very possible that the bug you care about wasn't fixed, and then you're installing the kernel on your system and you will break it because you haven't tested it during the release candidate cycles. And then we see something very similar with the stable and LTS releases, because when we cut LTS release candidates, we definitely get feedback of users testing it both on large and small systems, but that feedback is very limited, and there's this hope that somehow the bug that you care about would be fixed by someone else. This problem becomes worse the older the kernel gets, because as I said before, users really mostly run on the latest trees. There's diminishing amount of tests happening the older the kernel gets. We see quite a lot of feedback for the 6.6 tree currently and the 6.1 tree. If you look at the 4.14 tree or the 4.19 tree, only very few users actually test and report issues before we're able to release it, which is very unfortunate, because it means that we add bugs that we don't want to add into those old kernels, and we don't know that we added them until it breaks a real system. So maybe thinking about what we can do to improve this situation. And I think that when I started this talk, or when I just chat with people about this, about how we can make stable kernels more stable and how we can make LTS kernels more stable, usually I hear feedback that, we need to find a way to make those trees last for longer, right? So how do we make kernel trees stay active for 2 years, then for 6 years, 10 years, or how do we make them work for decades? Because that's what makes them stable, right? Like, we think that if we don't change the underlying kernel for a decade, then suddenly things will improve, and all we have to do is just find a way to make it happen. And to me, that's the opposite of what we want to do. We want to be able to support the trees where we have the most users, and we want to make sure that users are able to upgrade. The next one is that I mentioned before that the more we diverge from stream, the more difficult the process becomes. The harder it is to backport patches to it, the harder it is to test on it, and the harder it is to upgrade from that kernel, because the bigger the delta is, the harder the upgrade process is, because you will be hitting so many more issues that weren't tested before. And that's why when we do the backports to the LTS trees, we try and take as much as we can into them in the form of dependencies. So if we have a fix and it depends on 2 other patches, we will take the fix and the 2 other patches, which might not be stable material, but we do that so we will diverge less from upstream. The less we diverge, the easier the maintenance effort becomes. And the same thing goes to our users. If you are using the LTS trees, take the whole LTS tree, even if you might not care about half of it, right? If you don't care about half of it, there's no harm in taking that half. And in the case that you are mistaken and you actually do care about a patch or 2 in that half, then you got a free fix for it, right? There's no reason to cherry pick out of the LTS tree whatsoever. And another thing is to be part of the effort and kind of come in and help. For a project that is the biggest open source project in the world, we have so few folks who are actively participating in this release workflow. And it will be great to see more folks and more help and more support there. And this is for your own benefit, right? This happens for the benefit of the users at the end, and most of you here are the users. And if you don't test what we release, then we can't promise that we won't break you. Because this is really I believe that this is the only thing that the kernel community promises to its users, that it will never regress user space. And it's unfortunate to see that only so few users actually take advantage of that promise, because this is quite a strong promise, and this is probably the most important thing to users, right? We want our workloads to keep working. We want our products to keep doing what they're doing. We want our cars to keep driving. And if I can take advantage of this promise, I would definitely do that. And so this is a bit tricky because we're not trying to support more kernels for longer. We're not trying to get to the point where we can support 20 kernels over 20 years. This will be the opposite of where we're going for. What we want to do is to be able to support as few kernels. So we want to take a step back from the 6-year kernels we supported and try to cut it down to 4 and then see where it goes next. We want our users to be confident that they can upgrade. We want our users to run the latest LTS tree, and we want them to upgrade to the next LTS tree when it's been released at the end of the year. So if we're on 6.6, which was just released, we really wish that most of our users would be running on this 6.6 tree. The trick for getting away from very long kernel trees is just upgrading very often. So this is all nice and great, but some of us can't just take our products and upgrade them immediately. Sometimes we depend on the vendor. Sometimes we depend on a bunch of other circumstances that prevent us from being able just to upgrade to the latest LTS tree. And so while we say that it's something that you should be doing, you should be upgrading to the latest LTS tree, and you should be maybe even trying to use the latest stable tree as far as you can. It's really hard. And so some of the ways I would suggest to improve that process for like yourselves is, the first one is invest in your testing story. This is probably the single most important thing that the project can do for itself. The Linux kernel has realized that over the past 10 years, and there's this massive improvement in the testing story the kernel has, and we definitely saw issues going away. Even going back to about 20 years ago, systems like LogDep, for example, when SMP was introduced, helped eliminate classes of bugs that would have otherwise bitten us for forever. This investment into testing infrastructure, into tests, and the testing story overall is very important both to the Linux kernel as a project and to you all as users. This is critical. And I kind of split it up into 3 parts. The first one is quick smoke tests. It would be really great if you can be in sync with the kernel community releases. So if when Linus does his release candidates, it would be great if you can take them and test them out on your products to make sure it doesn't regress. When we do the LTS release candidates, it's wonderful if you can take your product and make sure that it still runs on that latest release candidate. The next one is whole system test, and it's something that's been very difficult to get. If there is a way where you can run your product, your system, whatever it is, and find a way to give feedback, both to the upstream community as well as to the LTS community, if things still work or if things still break. And it's fine to say, hey, I saw you release this release candidate, I tried my thing and it works. This is an awesome feedback. Things are working great, perfect. You don't have to wait until issues come up. Even just to hear that things are still working fine, it's really, really valuable. And the wider those tests are, the better the result is both for the kernel community as well as for the users. The more code paths we can exercise, the better it is in the long term to keep the stability of the kernel tree, both for ourselves and our users. The last one is bisection, and we saw it a lot with the both in the upstream community and the LTS tree, is that users sometimes see an issue when they upgrade. They might have upgraded to the latest kernel tree, and something broke for them. And just because we don't know what everyone are doing with the kernel, it's very hard for upstream developers to dig into what broke. Sometimes we see a random file system corruption or crashes, null pointer dereferences. Sometimes they're easier to debug, but sometimes they're very, very tricky. And from my observation, many of the issues that are not easy to reproduce are getting lost just because we don't know what everyone are doing with the kernels. So developing the ability to bisect within the kernel tree and run those tests on your products is really valuable. You will get a much better response if you are able to go to the upstream community and say, hey, my workload broke, and this is the commit that broke it. Can you please help me fix it? This is much better than just saying, hey, my workload broke. So developing the ability to do bisections is really, really important. If we can't upgrade, let's say we have this limitation where we can't go from one LTS to another, but we still want to make sure that we have that path forward. One thing we can do is, and I've been doing it in my capacity working in Google, is being able to run a set of our workloads on the latest LTS tree. So maybe we don't run the whole, the entirety of the workloads on the latest LTS tree. We might run 1% or 2% or 5% of our workloads on that LTS tree. It's a great way for us to weed out issues in that tree to make sure that they don't affect your product, but also for you as users, it's a great way to make sure that you have the path of upgrading from one tree to the other open. Because if you know that your workload can run on the latest LTS tree, then you know that you have the option of upgrading, that you're not blocked on something unknown. Because the worst thing to do here is to say, hey, I'm stuck on 5.4 for whatever reason, and I'm not sure why, but I can't upgrade. This is really a bad state to be in. So doing this proactively, just to shake out the bugs that show up in the latest LTS tree is a wonderful way to make sure that you have a path forward to upgrade. Another thing I've observed is that sometimes we're forced to do an upgrade. Sometimes the stars align and maybe the upstream LTS tree goes end of life, or sometimes we need a new feature that exists only in the latest LTS tree. Sometimes it might be a new product that we design and we decide to use whatever kernel version. And then at that point, we invest the efforts to move into that kernel and to stabilize it. And what I'm suggesting is that once we've made this jump, let's say we've upgraded from 5.10 to 6.1, and let's say we're happy in 6.1, don't take your foot off the gas pedal. If you're at 6.1, great, you've accomplished that upgrade. How do I get to the next kernel version? How do I go to 6x? I already know how to do this. I already did this right now. Jumping up one kernel version, let's keep doing it to get all the way to the end. This is a really great way to kind of create this culture of being able to upgrade on an annual cadence or maybe even more often. It also becomes very easy to upgrade if the delta is small. So going from a really ancient kernel to a really new kernel is difficult because there's so much more content, there's so much more new code that wasn't tested on your systems. It's really complicated. You will be hitting so many issues, and the more issues you hit at once, the more difficult it is to fix them. If you hit 10 separate issues all at once, you will have a hard time finding which issues are those really are and splitting them into individual ones and then fixing them. Where if you go from, where if the delta is small and you jump from one kernel to the next, and you might hit only 2 issues, and fixing those 2 issues is fairly straightforward because just how small they are, because the number is so small. The more the number grows, the effort needed grows exponentially to address them. The last one is to report stuff. We have seen so many cases of users who are stuck on an old kernel, and they have never told anyone, they have never said anything. Upgrading, like some users are stuck on like 5.10, and when they tried to upgrade, it broke their graphics card. So they never did, and they just decided to stay on 5.10. No one knows, and no one can help them. And so it's very important for us to be able to hear from you, to get feedback. And this is really, going back to the first slide, this is all about the users. This is all about you. You need to tell us if things are working or they're not working. And we're really trying to get as much feedback back as we can. Even if you just tell us, hey, things are working great for us, that's wonderful. But just please test and report it back. Yeah. Thank you. If you have questions, comments.
Thank you for your great talk. So I'm working for the embedded products, and what prevents us to use the upstream kernel is so-called vendor kernels, which is maintained by the SoC suppliers. So I think it makes really huge fragmentation. And is there any kind of activities on that program, or maybe some suggestions to deal with it?
Yep, this is definitely an issue we've been trying to tackle. I saw it myself many times. I think that Greg has been putting up an effort in the past decade or so with working with vendors and trying to get them to do the right thing. Has been running around between vendors, countries, entities, trying to get them to be aligned with the LTS tree. And I think we're slowly getting there. I think that if you have a certain vendor that is not playing well, you can try and contacting us directly to try and, in all seriousness. We've been trying to get everyone on the same page. And I'll tell you about a case earlier this year where I felt really good with myself. We're working with a certain vendor who is actually ahead of us, of the product I manage, and they were complaining to me that hey, why are you using the Sentient 6.1 kernel? You need to upgrade. So we're slowly getting there, but unfortunately this all comes back to the relationship you have with that vendor. If you can push that vendor to be better aligned with upstream, that's great. We've seen cases where companies do it on a contractual basis, where part of your contract is that you have to upgrade within a certain amount of weeks after the release of the upstream LTS, and also pressuring vendors to upstream their code, because you're stuck with the vendor tree because it has so much out of tree code. If you get that vendor to upstream all that code, your life will be much easier.
Thank you so much.
One question. I realize that it's I think it's quite interesting that you mentioned that when we upgrade our kernel, the GPU breaks. So is there, I think that's one of the things that's stopping us, because we are an R&D company, and then we try to test the, sometimes we try to use a newer kernel, and then with a different QDA version, and then things always break. So that's what's stopping us from always upgrading to the latest LTS. So is there anything working in the, on your side or on the back-end side that is like providing an archive saying that this new kernel supports this version of the GPU, things like that? Or because these are, I think, very prominent challenges that is stopping us from always upgrading our kernel. So what do you suggest?
Yeah, so we recently have something called the regression tracker upstream, which is a way for us to say that, hey, a certain functionality broke at a certain point, and we try and keep track of that. So I would say that if you try to upgrade, and you saw that a certain piece of hardware break, you can report it. There's a regression mailing list, and there's a very great community of people who try and help there, and they help us to try and track down those breakages, right? Because it shouldn't be the case that some GPUs work with some kernel versions. It should be the case that all GPUs work with all kernel versions, right? And so if at some point a certain GPU worked with a kernel and then it stopped working, then we want to find out why and we want to fix it. So we have the regression mailing list. I think it's regressions at, I'll find it, I can find it for you later. And it's a great, just report issues there and we'll try and fix them. And it really helps if you can pinpoint the specific kernel where things broke or the specific commit where things broke, because it sounds like you would be able to bisect the issue, right? And just those reports are really valuable.
Thanks, Sasha, for your important points. Share most of them. I have a question. How do you measure your users of the older kernels? Also, given that some of them are indirect users. The challenge always is with users, they only speak up when something is broken, at most, sometimes even not then. And I guess the LTS kernel is also indirectly used quite heavily downstreams by, you mentioned them, vendor kernels, but also in-house kernels, which are based on LTS at least. So do you have some numbers on that?
We don't. We have no kernel communities, and we don't know who does what. Our guesstimates of how many users we have are based both on what you said of how many users come and say that we're using it, but also on our kind of knowledge of the world. So we know, for example, Android uses this kernel version, Chrome uses that kernel version. A lot of it is guesstimates that we have to know where we are. But that's why we're asking for feedback from users. We want folks to come back and tell us, hey, I'm using this kernel version and it works for me. This is an awesome feedback. It's so appreciated. And I don't think as many people realize just how good it is.
Hi, thanks for a good talk. So I think one of the indirect motivation of using an old kernel is that people want to use old distro because they don't want incompatibility inside userland. For example, they want to use an old GCC package that is supported on old Debian, so they use old kernel without knowing. Do you have any insights about that?
Yep. So about 12 years ago, there was a kernel summit in Cambridge, Massachusetts. And the one thing that came out from that summit was what's called the Cambridge Promise. And Linus stated very clearly, the kernel will never break user space. The single thing that the kernel community promises to user space, it will not break it. If you see cases where upgrading to a new kernel version breaks your user space, and it's a real scenario, right? You have a real user space package that stops working as you upgraded your kernel, please report to it. Linus has gone through above and beyond to fix these issues. He reverted entire patches of code. He did crazy things to make user space keep working. This is the #1 priority of the kernel. So if you don't feel comfortable upgrading because you're afraid the user space will break, go if you identify such an issue, please report it.
Yeah, sorry, I know about the promise, but yeah. People, if they want, can upgrade the kernel that is used by old distro, but the only way they can upgrade the kernel is upgrading the whole distro, because they don't have an ability to build a kernel by themselves.
At that point, it depends on your distro vendor. At that point, you should pressure your distro vendor to help you or upgrade to a new version of the distro. That's kind of the relationship between you and your distro.
Yeah, thank you.
Excuse me. I'm a Debian developer, so I want to say about the Debian. Debian uses only LTS kernels, not old kernel versions. So, and we provide backport kernel packages, so you can use the newer kernel versions without upgrading whole distros.
Yes, in general, I would recommend using distros as similar as Debian rather than more enterprise distros that tend to be stuck on a kernel that's 10 years old. and it's kind of Franken kernel that barely keeps chugging along. Debian has been a great part of the community, and I wish that more distros would be doing it as well as Debian does.
Hi, Sasha. Thanks for the talk. So what do you think is the sweet spots for the LTS tenure support? 4 years or?
Depends on the community. It's really not up to us, right? It depends on how much the community, if the community is there or not. It's not like something that.
Okay.
If the people are there, we'll support it. But so far, it doesn't look like enough people care about old kernels, which is fine.
Yeah, typically it depends on the sector. Like auto customers tend to stick on for long. Some of the customers want a migration every year. So, okay.
And I think we're running out of time, so I will call it. Thank you very much.
Thanks for the talk. You mentioned there's a regression link or something. We tried to help also by submitting our reports, whatever we found. Any keywords you can find, then I can take further. You don't have to say exactly.
So if you're at Word, I want to give you
I can take a photo.
I have.
Do you have the
yes,
HDMI? Yes. Yes. Good.
Yeah, I was here last year too. No, but you're also good because you're getting there, and I think that you guys have solid plans of getting rid of it as far as I remember.
Huh?
So Jesse like 3 weeks.
Just 没有啊，他这次没有来。
I might stop by on Thursday. I saw you're working on trace and stuff. You're so busy. How is that done? I couldn't get the audio. So I want to get you to mention. It wasn't. So we never said 2 years. like it was a bit the patch I sent to update the website to take it down from to like I guess it's also like so everyone because we're trying to get to 2 years. Let's say we can do 2 years. It was a bit like I need to be more careful with my support, but we're not going to go to 2 years with all. So we're going to 4 years. This should be fine. No real problem. Let's see how it goes. I don't think we'll get down to 2 years. I think it will take some more time.
And hi everyone, and my name is Yanfu Chen, and I come from National Chen Kung University in Taiwan. And today's my presentation is about a secure and efficient RISC-V-based simulator. And this is today's agenda. Okay. So first, I will introduce our motivation. So initially, we want to find a RISC-V-based simulator for computer architecture course. But because the RISC-V CPU is not easy to access, but some existing RISC-V-based simulator like QEMU or Spike is too complex to be a teaching material. So we decided to construct a compact and efficient simulator from scratch. And the compact means small and simple, and we control the total project size and make it more readable for students. However, the compact also means slow. So our another goal is to improve the performance of simulator and lower its memory usage. And furthermore, we implemented a baseline just-in-time compiler to further improve the performance of our simulator. Okay, and this page summarizes our achievement. We choose two popular open source RISC-V simulator to compare our performance. And for interpreter-only design, the comparing target is Spike, and our performance outperforms the Spike in all cases. And our project is RV32EMU. And for the just-in-time compiler, our comparing target is QEMU. And unlike the dynamic binary translation of QEMU, we don't need to write any assembly code when integrating the just-in-time compiler. And nevertheless, our performance is very close to QEMU and even outperforms it in some cases. And our project also supports for RV32IM ACF extension and several SDL-based system calls for running video games. And we also support for remote GDB debugging. Okay. And this page shows some classic PC game can run smoothly on our simulator. And next, I will introduce the detail of our design. But before that, I want to share our design concept. And the first design concept is we want to improve the performance of our simulator. So we utilize some techniques of modern compiler, and we make some improvement based on the RISC-V architecture property and modern computer architecture view. And the second concept is we want to realize the tier just-in-time compilation. So for tier just-in-time compilation, we may have an interpreter, tier 1 just-in-time compiler, and tier 2 just-in-time compiler. So we need a profiler to collect the profiling data for launch the just-in-time compilation process. And the profiler in our simulator is the interpreter. And we also need a baseline just-in-time compiler to evaluate the effectiveness of integrating the just-in-time compiler. So I will introduce our baseline just-in-time compiler later. And because we save the profiling data, and the memory usage of providing data may increase during emulation. So we also have some strategy to lower the memory usage. And the last concept is we want to create a secure sandbox execution environment. So we keep our design of interpreter simple and make it execute securely without runtime generated machine code. Okay. So, and in this page, I will explain the reason why our simulator mode can make the secure execution. And the first reason is simplicity, because the implementation of our interpreter is relatively simple and we keep all components as straightforward. So the simplicity enhances the security by reducing the attack surface. And the second reason is unlike the dynamic binary translation or just-in-time compilation, the interpreter makes secure execution without invoking runtime generated machine code. So the attacker cannot attack our interpreter mode with changing the runtime generated machine code, but they can do so in dynamic binary translation or just-in-time compilation. And the third reason is we make comprehensive testing procedure across all aspects of the module within interpreter system. So that's the reason why our interpreter can make secure execution. And also, the interpreter serves as the profiler in our simulator. So the interpreter mode is very important for our simulator. Okay, so next I will introduce the architecture of our interpreter. First, we have a ELF loader, and ELF loader load the user RISC-V program compiled by RISC-V toolchain. Then we have two main modules. First is block translation module, and the second is block emulation module. Block translation module emulates the stage of instruction fetching, instruction decoding, and instruction dispatching. And we divided the ELF file into several basic blocks. So the decoding information from instruction decoding and the emulation function from instruction dispatching are stored in the basic block data structure. And after the translation, we pass the basic block data structure to the block emulation module. And block emulation module emulates the stage of instruction execution. So the block emulation module simply invokes the emulation function from the instruction dispatching. And the parameter of emulation function is decoding function. Okay. And next, I will introduce some technique we use to improve our performance. And the first technique is tail call optimization. So if your recursive function have the same number of parameter and the same parameter type and same function return type, you can launch the tail call optimization. And when invoking the recursive function, tail call optimization eliminates the need for the creation of new function stack frame. And we can reuse the current function stack frame to execute next function. So we can see the example below. In the first example, we don't launch the tail call optimization in this recursive function. So we can see from this instruction sequence, we need to maintain the stack pointer register to create a new function stack frame. And we use the call instruction. Call instruction recall the return address and jump to the next function. By contrast, in the second example, we launch the tail call optimization with a compiler hint. So in this instruction sequence, we don't need to maintain any register pointer. We don't need to maintain any stack pointer register. We directly jump to the next function. So the tail call optimization helps us to save the overhead of creating new function stack frame. Okay. Okay, so to launch the tail call optimization, we rewrite our emulation function into self-re. And to launch the tail call optimization, we rewrite our emulation function into self-recursive version and introduce a compiler hint. So with this modification, all the emulation function within a base block can reuse the same function stack frame to execute. And we can see the example below is our emulation function about an NOP instruction. And in this instruction sequence, we don't need to maintain any stack pointer register, and we don't need to recall the return address. We just directly jump to the next emulation function here. And the second technique to improve the performance is block chaining. Block chaining connects the basic block along an execution path, and it significantly improves the performance of locating next block. So for example, after we emulating a basic block, we need to back to the translation module from emulation module, then finding or translating the next basic block, and back to the emulation module. However, we want to save the overhead of switching between emulation module and translation module. So that's the reason why we implemented the block chaining. And in the end of a basic block, the instruction must be a branch instruction or jump instruction. And we divided this instruction into two categories. The first category is direct jump and branch, because the target of direct jump and branch is constant. So we can simply change the previous block to the current block. And the second category is indirect jump, because the jump target of indirect jump is determined by register value, so it is inconstant. And we implemented a branch history table. If we can locate the next block in the branch history table, we directly jump to it. But if not, we should back to the emulation and translation module. And we can see from this example. So after we emulating this basic block, we can get the branch result, maybe branch taken or branch untaken. So if branch taken, we can directly jump to this basic block. And if branch untaken, we can directly jump to this basic block in the emulation module. So the block chaining saves the overhead of switching between the emulation module and translation module. Okay, and the third technique is macro operation fusion. And macro operation fusion is a common technique in modern compiler design. So how does the macro operation benefit our simulator? The reason is our simulator is a functional simulator. So it only cares about the final result. It don't care about the process of emulation. So we can create a filter function to emulate several instructions with a function code. For example, if we want to emulate 3 instructions, we need to invoke the emulation function 3 times previously. But with the macro operation fusion, if we want to emulate 3 instructions, we can invoke a filter function to emulate these 3 instructions. So the macro operation fusion saves the overhead of function code. And we referred the reports on macro operation fusion for RISC-V and examined the instruction pattern of our benchmarks. And finally, we choose several candidates occurs frequently. And this table shows the candidate we choose. And for example, the first candidate is AUIPC instruction and ADDI instruction. In the RISC-V architecture, if you want to create a constant, you need a AUIPC instruction and ADDI instruction. And for the function prolog and function flog of RISC-V architecture, you need continuous lower and continuous lower. So that's the reason why this instruction pattern occurs frequently. Okay, and this table shows the dynamic instruction count with and without the macro operation fusion. And the first column is our benchmark, and the second column is the dynamic instruction count without the macro operation fusion. And this is the dynamic instruction count with the macro operation fusion. And this is the reduction in the dynamic instruction count. We can see from the next column, the macro operation fusion effectively reduced the number of instructions to be executed. And this also means the number of function code we save. Okay, and the next strategy to improve the performance is C routine substitution. Because our benchmarks are generating from the compilation of C program. So some standard library function like memory copy and memory set occurs frequently. And we observed that the instruction sequence of this standard library function is constant if your program are compiled by the same OS and the same compiler. So we recorded the instruction sequence as reference target and substitute as it if the pattern match. So we can gain the performance from this because emulating while standard library function is much slower than directly invoking the whole standard library function. Okay, and the next strategy to improve the performance is manipulating frequently updated CPU state by register. And during the emulation, we keep updating the emulating CPU state, including program counter, CPU cycle, register value, and so on. And especially the program counter and CPU cycle should be updated every time we emulate an instruction. And these two variables stored in a emulated CPU state data structure. So the reference of the program counter and CPU cycle need a memory operation. From modern architecture view, the overhead of memory operation is heavier than register operation. To solve this, we pass the program counter and CPU cycle as parameter for emulation function, and we only update that in the end of the emulation. And we can see the example below. The left side is the original version, and right side is the modified version. In the original version, to add instruction to update the CPU cycle and program counter is a memory operation. But in the modified version, to add instructions to update the CPU cycle and program counter is register operation. So we can gain the performance improvement from this because register operation is faster than memory operation. Okay. And we also have some strategy to reduce the memory usage and footprint because we store the providing data like basic block data structure. And the number of basic block data structure would increase during the emulation. And to limit the total number of basic block, we introduced a block cache. And we implemented 3 different cache replacement policy to evaluate its performance. And LRU is the first place, LFU is the second place, and the last is adaptive replacement cache. Because its replacement policy algorithm is too complex. But finally, we choose the LFU policy because of the just-in-time compilation. And in the just-in-time compilation, we need to detect the hotspot. And in the LFU cache, we record the frequency, using frequency of a basic block. So we can use it to detect the hotspot. If the using frequency of a basic block exceeds the predetermined threshold, we launch the just-in-time compilation process. So that's the reason why we choose LFU cache finally. And also, we have some strategy to limit the memory footprint. So we introduce a memory pool, and this memory pool manages the deallocation and the allocation of basic block data structure. Okay, so next I will show the experimental result of our interpreter. And this is our benchmark, and we can see this is the percentage of the ALU instructions. And this is the percentage of memory IO instruction. And it may be load or store instruction. And this is the percentage of branch instruction, maybe indirect jump, or branch. And this is the dynamic instruction count of the benchmark. Okay, so this figure shows the normalized execution time of Spike and RV32 EMU. And we can see from this figure, the performance of our project outperforms Spike in all cases, especially in the Mandelbrot benchmark and Price benchmark. And the reason is because the branch instruction percentage in this benchmark is high. So the block chaining effectively enhances the performance of locating next basic block and jump to it in the emulation module. We save the overhead of switching between translation module and emulation module. However, we can see the SHA benchmark. In this benchmark, the performance of our project is very close to Spike. And this is because the percentage of branch instruction in this benchmark is only 1%. Okay. So here I summarize the strategy in interpreter. So the performance of our interpreter outperforms Spike. And to improve the performance, we apply tailcode optimization, block chaining, macro operation fusion, C-routine substitution, and manipulate frequently updating CPU state by register. And for reducing the memory usage and footprint, we introduced LFU cache and memory pool. Okay. So next, I will introduce our baseline just-in-time compiler. And before implement the tiered compilation, we need to baseline just-in-time compiler to evaluate our performance of integrated just-in-time compiler. And the baseline means we want to use minimal effort to implement it. We don't want to write any assembly code, and we don't want to modify the design of interpreter. Okay. So the concept of just-in-time compiler is we want to lower the emulation overhead. We want to create an emulation function, emulates all the instructions along a hard execution path. So you can imagine we want to create a very huge fused function. And all the variable in the emulation function can be replaced with the constant value because we have the decoding information in code generation stage. So with this replacement, the compiler can make further optimization to generate optimized machine code. And the second concept is our just-in-time compiler only for hotspot because the overhead of runtime code generation and compilation is significant. So if we launch the just-in-time compiler for code execution path, the overhead of code generation and compilation and runtime may outweigh the benefits. Okay, and this is the implementation of our baseline just-in-time compiler. For interpreter, we have implemented the block chaining and LFU cache. So for the baseline just-in-time compiler, we only need to add 3 additional modules. The first is code generation module. And we trace the trendy block pack and pass the emulation module, and pass the emulation function and decoding information to the code generator. And code generator generate the C code like this example. This is the program counter of the current instruction. And this is the program counter of the next instruction. Between this label, this C code is emulation function. Originally, the register value or the immediate in the emulation function is variable. But in code generation stage, we have decoding information. So we can replace this variable with the constant value. And compiler can make further optimization. And for example, compiler can make constant propagation or constant floating. And after we generating this C code, we should have an integrated compiler to compile them. And the compiler we integrated here is clan. We pass the C code to the clan, and clan compile the C code to the machine code. And this machine code is a fused function to emulate all the instruction within a hard execution path. And after the clan generated the machine code, we store this machine code into a code cache for future use. And the example below is the workflow of our just-in-time compiler. So the LFU cache records the using frequency of the basic block. And if we detect a using frequency of a basic block exceeds the predetermined threshold, we launch the just-in-time compiler process. And just-in-time compiler traces the trending block and pass the emulation function and decoding information to the C code generator. And C code generator generates a C code like the example above. And we pass this C code to the clan. Then clan compile the C code. And we add C code into machine code. And we store this machine code into the code cache for future use. And this is the architecture after integrated the just-in-time compiler. The upper part is interpreter design. The lower part is just-in-time compiler. And we can see from this figure, we don't need to modify the design of interpreter when integrated the just-in-time compiler. Okay, and this figure also shows the normalized time of QEMU and RB32EMU because the comparing target of just-in-time compiler is QEMU. And we can see from this figure, the performance of our just-in-time compiler is very close to QEMU in most cases. And we even outperform it in some cases like FP emulation and stream. However, in some cases like price or big field, the performance of our simulator is much lower than QEMU. And that's because we cannot detect the specific hotspot in this benchmark. So the just-in-time compiler are not invoked in these two benchmarks. And that's the reason why the performance of RB32EMU is much lower than QEMU in these two benchmarks. And it is also the disadvantage of our baseline just-in-time compiler design, because the just-in-time compiler only launch when we detect the specific hotspot. Okay, and in addition to the instruction set simulator RB32EMU, we have another system emulation project, CMU. As shown in this video, the upstream Linux kernel, RISC-V Linux kernel, can run smoothly on the CMU without any code change. And CMU also supports for memory management unit environment and supports for virtual I/O or virtual GPU. Considering the development, we separate the instruction set simulator RB32EMU and system simulator CMU into two projects. But recently, we plan to integrate them. Okay. So in conclusion, our project RB32EMU is a compact and efficient open source simulator. And it has a fast interpreter and baseline just-in-time compiler. Moreover, it only implemented in about 10,000 C code. This project is relatively simple and small, and its performance is acceptable. There are some ongoing tasks like tiered compilation and support for RISC-V vector extension. So, if you have any interest in our project, you can scan this QR code or contact this email. Thank you.
So I have two questions. One is, you mentioned about security.
Okay, and
you talked about, you mentioned about security, but you did not talk that much about security, right?
Yeah, yes.
So can you tell us a little bit more about security?
Okay. And the main security of our interpreter is big. Okay. The main security issue about our simulator is because in the QEMU, it uses dynamic binary translation, and for the just-in-time compilation, and they also need a runtime generated machine code, and the attacker can change the runtime generated machine code to attack you. But in our interpreter, we don't invoke the runtime generated machine code, so the execution of interpreter is relatively secure.
So the just-in-time compilation in your system does not happen runtime? I didn't get it.
And because the just-in-time compilation mode also have the secure issue. So if you are care about the secure, you can close the just-in-time compiler mode in our configuration.
I see, okay, thank you. And one more question, if anyone doesn't have one. So you talk about CPU cycles, right?
Yes.
So you intend to present the CPU cycle to the user so that the user can see it?
And if user want to get the CPU cycle, you can print this information.
Right. Yeah, but the problem is that you do not emulate the cache and memory. So the CPU cycle may not mean anything because
Yes,
you don't count like memory
yeah,
stores,
and because we emulate a single cycle CPU, so it may complete all things in a cycle. So all the stage of instruction fetching, instruction decoding, instruction dispatching, and instruction execution complete, and we count one cycle. So this is not a performance model.
I see. So if you assume single cycle CPU,
yes,
that CPU cycle is correct, like accurate.
Yes.
Okay, okay, thank you.
Okay, thanks for the presentation. Then I have two questions about the host systems. So as far as I remember, you showed the results on the x86 platform running their emulation.
Yes.
So do you have any plan to support the other architectures like ARM or RISC-V?
Oh, okay. We have the experimental result on the ARM host machine, and the figure is in our theory, and not shown in here. Yes. So if you want, I can provide you later.
Okay. So and then the other question is the depends on the host CPU cache size. So if the interpreter core code or JIT compiled code can be fit in the cache line, so that will be a great performance improvement, I guess. So do you see any cache size dependency?
Okay. And so for the cache size, we make some experiment in the cache size. And finally, we choose 1024 for the cache size. And this is the experimental result. Yes.
Okay, I see. Good. Okay, thank you.
So you talked a lot about what you've done so far, but you haven't talked so much about what's next for this.
Okay. Okay, and what you go next is the tiered compilation. And the tiered compilation, we have we only have a baseline just-in-time compiler. But the runtime code generation and compilation of Clang is the compile time for Clang is so long. So we want to integrate a tier 1 compiler. The compile time of tier 1 compiler is short, but the quality of its machine code is not good. But because its compile time is short, so we can translate the basic block to the host machine code as soon as possible. And if we find this machine code invoked by the tier 1 compiler frequently, we can use the tier 2 compiler. And the compile time of tier 2 compiler is long, but the quality of the machine code is very good. It made more optimization on this generated C code. Yes.
Are you expecting that that's going to be a hard thing to implement? Difficult thing to implement?
Yes, because it is too difficult to find a runtime compiler, and its compile time is short. So now we still finding that. Yes.
Okay. Thank you.
Thank you for your presentation. I have one question. In your just-in-time compiler, how do you do C code generation? Use libraries or handmade?
It just use a string library, and we use string cat to create a string, and the content of string is the C code. Yes, and we pass this string to the Clang, and Clang compile it to machine code. Yes.
Thank you.
Anyone else?
Okay. Okay. Thank you. Thank you, everyone.
similar job as yours.
Java.
At the time, the Java was a very hot language.
Yes.
My job was to, optimize the Java virtual machine system to run the Java bytecodes on the specific CPU. So I did the interpreter.
We also learned the just-in-time compilation from the Java virtual machine.
And I really optimized the direct Java, indirect Java between each bytecode injection code. So your presentation really reminded me what I did.
Okay.
So that was a lot of fun.
So it is a common technique in some fast virtual machine, blockchain.
Yeah, so I read some papers, some trials.
Okay.
Now you're doing that for this fight. So it was just fun to listen to. Thank you.
Thank you. Thank you.
check your laptop with
Yeah.
connected? Yeah. So you first, second.
Okay.
ちょっと何かおかしい気がするけど、今のところなんか時々映らなくなるんですね。
でも
今は映ってますね。はい。これとはこっちのいるか。よいしょと。
事前準備は本当重要です。
そうですね。これがレーザーポイントかな。
人によっては変換アダプターがないとつなげる
はいはいはいはい。
変換アダプターください。
そうですね。
っていうふうに今日言われて、一人スタッフが秋葉原に帰り始めました。で帰ってきたら他の人に借りてて、いらなくなったっていうですね。
かわいそう。
ちょうど始まった時来て間に合わなかったか。
ああ、それはかわいそうに。まあまあね、気持ちはわかるけど。
そうそう。お疲れ様っていう。
そうですね。この PC セキュリティが厳しくってね。
すごいあるあると思います。
そうなんですよ。64。まだかな。うん、ファイルを分割して収納しないとこうなくしたらこうセキュリティ重大問題だからみたいな感じで、なんかねいろいろガードがかかってるんですね。そうなんですよ。
Does there happen to be Ethernet port there or not? Only wireless?
Just wireless.
Okay. I'm actually using Fujitsu.
Oh, I'm glad to see.
And you can access the Wi-Fi.
Okay. I guess I'll try connect back.
ごいでしょう。かかってると思いますよ。うん、そんでもこうね、なくしちゃうと大ごとになって、また社長が怒られるからこんなことになったんでしょうね。とんでもねえって。うん。OK、やっとだ。まだワンドライブが動いてね。おし動いた。これでどうだ。クソか。即されていませんか。つながってるはずだけど。多分うん。そうなんです。はいはい。と思ったら志賀さん今日私の聞いていかないんですか。それはだって聞いておかないと。はい。でこれで多分スライドショーすれば大丈夫かな。大丈夫っぽいですね。
です。
はい。じゃあちょっとよいしょ。Your turn.
Ah.
バッテリーが足りないというところにいます。あるあるですね。昨日のオープン SSF で残り 5% だった。
Is this yours? No?
No,
It's from offer. Oh, okay.
But
someone else, I guess.
This is the order from the staff, I guess.
Oh, I guess that.
But
yeah, because that is better than mine.
なんだこれ。
誰か一旦じゃあちょっと回収します。はい。Lost and found.
Yeah. So this is the mic we're using, right?
And also there the guiding speakers. So
Okay.
they didn't check it. We show the 5 minutes, 3 minutes, 1 minute. Stop.
Okay.
So don't miss that.
Okay. Let's see. Right. Okay, yeah, everything seems to work. I hope it'll keep working.
もうセキュリティファットなもんで、もうスタッフの人がびっくりされてガチガチに固められてて勘弁してほしいっすね、本当にもう。
プレゼン中に穴出てきたら困っちゃいます。
困っちゃいますよ、本当に。うん、終わる気がするけどな。もうちょい。正直体調悪いんですよね。風邪ひいたっぽくて。このリーナスとの会談が控えてるっていう地獄ですかみたいな。終わったっぽいな。よし。はい、はい、はい、はい。あ、はい。QA 繰り返せるかなそんなに語学力ないんですよね。はい。
これとか使わないですよ。
一応これだけでやっちゃおうかなと。はい。
わかりました。
はい。
じゃあ何かあったら言ってください。
あ、はい。
いや、僕も富士通にいるんですけど、昔統合職員です。
あ、そうなんですね。
はい、ISM やってます。
なるほど。
昔浅場さんの下にいて。
そうなんですね。
っていうのは会社休んでボランティアやってます。
お疲れ様です。エレクシー。意外と人少ないな。あちこちで喋ってるから。 うちがいるんだこれ。もう始めてもう適当に始めちゃってもいいですか？ちょっと遅れてるっぽいですね、この時計。May I start? Okay, let's talk about the CX, Computer Express Link, the next generation interconnect overview, and the status of Linux. Please let me myself. My name is Yasunori Goto. I have worked for Linux and related OSS since 2002. I developed for memory hotplug feature of Linux kernel, and I worked for technical support for troubles of Linux kernel, and etc. And currently, I am a leader of Fujitsu Linux kernel development teams. For some years, I have mainly worked for persistent memory, and I presented some praise about persistent memory, like here. And currently, my team has been working on CXL since April 2023. Please note the followings. Please refer the CXL specification for proper understanding. Anyone can download the CXL specification from official site. What you need is only registering your name and email address to the site. Though I try to make sure there is no mistakes in my presentation, there might be misunderstandings or inaccuracies yet. The CXL specification and related specification are very huge, and I could read only some parts of them. CXL 3.1 is 1,166 pages, and related specification is very huge. So if you can find mistakes, please let me know. And I recommend it for you to study PCI or PCI Express and ACPI specification beforehand. The CXL specification is too difficult if you don't know them. Anyway, I hope my presentation helps you to understand CXL. Here is today's contents. At first, I'd like to talk about overview of CXL specification until 2.0 and additional specification of CXL 3.0 and 3.1. And finally, I'd like to talk about the status of the current Linux for CXL, memory tiering, and memory hotplug or memory pool. Okay, let's start about the overview of CXL until 2.0. What is Computer Express Link? It's a new specification of interconnect which connects devices like PCI Express. CXL is abbreviation of Computer Express Link. Official white paper says an open industry standard interconnect offering high bandwidth, low latency connectivity. It's suitable to connect a smart device like GPU, smart NIC, FPGA, computational storage, and so on. In addition, it's also useful to expand memory, volatile memory, and persistent memory. The newest revision of the specification is 3.1, which was released last month 14th. CXL seems to be winner against other competing specifications. The board of directors of CXL includes numerous vendors and service providers, Alibaba, AMD, ARM, Cisco, and blah, 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 and Meta, and Intel, and Microsoft, and so on. Other competing specifications seem not to be promising. OpenCopy and GenG were assimilated into CXL. And CCIX is not active. There is no new information after 2019 in CCIX press release. Since the promoter companies of CCIX are also members of CXL, so they can select CXL instead of CCIX. So why CXL become necessary? The first reason is increasing demand for fast processing of data. It's influencing of current technology trends such as machine learning. The second reason is the need to offload processing due to reaching limitation of CPU performance enhancement. GPGPU, FPGA, or SmartNIC must handle the processing instead. And finally, memory capacity must be increased. Though the number of CPU core increases, memory capacity does not follow it. Since DDR is a parallel interface, it's difficult to increase the number of CPU pins to connect more memory. So, new interconnect becomes necessary to connect devices and memories instead of PCI Express or DDR. So what is the advantage of CXL? Here is an example of calculation of GPGPU will be more effective. So far, a CPU and device must transfer data and instruction in bulk between DDR DRAM and GPGPU memory. Not only data, but also instructions for GPGPU must be transferred. It's a bit troublesome and need time for the transfer. CXL allows that CPU and GPGPU can access other size memory interactively. It will be effective for machine learning or any other modern analysis. Similar benefits can be obtained when you offload data processing to FPGA or SmartNIC. To access each other's memory effectively, not only CPU, but also devices require the use of cache to access memory from the other side interactively. Currently, PCI Express does not allow the use of cache for transfer data. Even if device memory is mapped to the host address space, CPU must use write-through access, which is slow. Devices need to transfer their data in bulk by DMA, which is not possible to interactively load and write memory. So there are requirements against the above limitation. CPUs and devices want to have interactive access using cache. They want to write back their cache when it's necessary. So CXL is created for the above requirements. So CXL web page also says the following. Computer Express Link is industrially support cache coherent interconnect for processors, memory expansion, and accelerators. But what is cache coherent here? So far, only CPUs must negotiate cache information for memory access each other. There are some famous protocols for cache coherency. For example, Meshi and Moeshi. Meshi's M means modified, and E is exclusive and shared and invalid. To access each other between CPUs and devices with cache, the devices also need to coordinate cache information with CPUs. CXL realizes it with Meshi protocol. Here is the characteristics of CXL. CXL utilizes CPI Express specification generation 5.0 or later. Its physical layer is same with PCI Express, but upper layer becomes CXL original protocol. PCI Express generation 5.0 or later allows different protocols, packet on its bus. CXL protocol is a mixture of the following three types of protocols. CXL-IO is used for CXL device detection, error report by PCI Express way. CXL cache is used to request or communicate cache information between devices and accelerators and CPUs. And CPU mem used to request for memory access between devices, accelerators, and CPUs. CXL-IO is same protocol with PCI Express, but others are new protocol of CXL. There are three definitions of device type of CXL. Type 1 device is it has a cache and does not have memory, or its inside memory is not shown to host. For example, SmartNIC or FPGA, which has the above structure. It uses protocol of CXL-IO and CXL cache. Type 2 device is which shows cache and memory to host. It's good example is GPGPU or FPGA, which shows device internal memory to host. This type device use all of protocol, CXL-IO, CXL cache, and CXL mem. And type 3 device is memory expansion, which connects CXL. It's for volatile memory and or persistent memory. It uses CXL-IO and CXL mem. CXL type 2 device manages their cache status by a device coherence engine, DCOH. It's a component in the device, and it must maintain status of cache of the device and memory access. Device memory, which is included in the device and it's shown to host, is called host-managed device memory. How to access from a type 2 device to HDMI is here. A CXL device needs to select the following status to access its memory, which is shown to host CPU. The first one is host bias state. Device needs to request CPUs to keep cache coherency before accessing device-attached memory. Like this green arrow, it must send a request to host CPU once, then it can access device-attached memory. Next one is a device bias state. Device can access device-attached memory without consulting the host coherency engines. After bias flip, this green arrow, device can access ideal latency and bandwidth. CXL 3.0 specification added another way. I'll talk it later. I need to talk about the features of Type 3 memory device. The following configuration is available. You can configure device as memory pool as follows. Use one memory device to one memory region, and bind multiple device to single memory region, and divide one device to multiple regions. In addition, interleave is available. This example is 8-way interleave by host bridge and CXL switches. CXL has binding of port of CXL switch. So far, upstream port must be only one in a PCI Express switch. However, a CXL switch can have multiple upstream ports in it. You can bind a downstream port to upstream port dynamically. To configure binding, a component which is called as Fabric Manager is necessary. Fabric Manager can be implemented to any style like the following. Software which running on host machine, embedded software running on a BMC like a server management software, embedded firmware running on another CXL device, and state machine running within the CXL device itself. Type 3 memory device can be divided into multiple regions as logical device. and assigned to different hosts. In this figure, type 3 device is divided to two logical devices. Logical device 1 and logical device 2 can be bound to different upstream ports. These upstream ports may be connected to different hosts. The fabric manager is responsible for dividing logical device and binding them to each port. In addition, hot plug is supported. CXL 2.0 devices will be hot pluggable like PCI Express device. It means CXL Type 3 memory device will be hot pluggable. Not only persistent memory, but also volatile memory will be hot pluggable as the hardware specification. In past, Fujitsu made special servers which support volatile memory hot plug. Memory hot plug of Linux kernel was developed for it at first, but many servers may support memory hot plug by CXL in future. Not only replacing a physical device, but you can add memory area which is hotly moved from another server. It will be important feature for memory pool. Here is a memory pool use case. Memory pool distributes a part of its regions to other servers as needed. Example of old use case of banking system is here. In daylight, it gives much memory to servers which access ATM transaction, and in night, it gives memory to other servers which processes batch jobs like payroll transfer. So far, this feature is only possible by a special server which supports memory hot plug. Another option is to use virtual machine on the same host, but it's not possible to pass a memory area to other hosts. CXL make it possible by establishing an open standard specification. And next use case is failover. A server can take over regions previously used by another failed server. Not only memory, but also a GPU may be able to take over its processing in future. Okay, next section is CXL 3.0 and 3.1, specification updates. Here is a list of new features of CXL 3.0. It was released 1 year ago, August 1st. The right table is quoted from its white paper. Personally, notable feature is fabric capabilities and memory sharing and enhanced coherency. And there is another thing update. It is twice speed than 2.0, but it just comes from PCI Express 6.0 specification. And multi-level switching is supported. It allowing CXL switch hierarchies. And direct memory access for peer-to-peer is supported by 3.0, and etc. But today, I'll talk about the 3 features which are notable, I think. The first one is fabric capability. Fabric connection is supported. The topology of connection was a tree structure whose root was one root port until CXL 2.0. Even dynamic binding is available. Tree structure is same with PCI Express. CXL 3.0 allows fabric connection via CXL switch like the right figure. The number of maximum nodes is 4,069, 1996. It can connect CXL devices with the shortest distance between servers. This is the most notable new feature for me. It will be basis of the next generation of distributed computing. Port-based routing is introduced for this capability. Messages in the fabric are sent with the port IDs of source and destination. Each ID is 12-bit for 4096 nodes. If a CXL switch supports port-based routing, it's called PBR switch. And a fabric manager needs to distribute IDs to PBR switch via management network. What is management network is, it can be SM bus, I2C, I3C, or Ethernet. All of them is okay. Next feature is enhanced coherency. CXL 3.0 allows that a device can have cache coherency information. In CXL 2.0, only CPU needs to maintain it. Devices need to ask CPUs to access its memory beforehand. In other words, CPUs and CXL devices have asymmetric relationship for cache coherency. In CXL 3.0, the relationship between CPUs and devices is symmetric. The DCOH of device watches cache coherency information on CXL. In addition, the device can request CPUs to update their cache information if necessary. For this purpose, back invalidation SNP BISNP channel is added to CXL memo protocol. Here is an example of enhanced coherency. Specification describes a variety of access patterns and timing between a CPU and device. This figure is simplified example of BISNP protocol. At first, CPU would like to access data address X of data, but device needed to flash cache address Y and request its data. So before getting data X, CPU must write the address data Y. After that, device can provide its data of X. So device can actively request CPU to change cache state and transfer data depending on the device state, like this figure. To confirm more correct sequence, please see this section in the spec. This is very interesting, I think. It describes various sequences, and you can understand how cache is managed actually. And please check it. And finally, next one feature is memory sharing. Memory sharing between hosts is available. Each host can work together by shared memory. Fabric Manager has a role of configuration of which memory regions to share and how to share them. There are two ways how to manage cache coherency. Multi-host hardware coherency. CXL device has a feature to manage cache coherency, and when a CPU requests data write to a device memory, the device needs to coordinate cache information of other host CPUs. Next one is software managed coherency. Software needs to manage cache coherency between hosts by itself. Even if the device does not have mechanism to coordinate cache coherency, this way is available. The actual mechanism by which software coordinates cache information is out of the scope of the CXL specification. Here is an update of CXL 3.0, its summary. Today, I'll briefly outline some of update features. Fabric enhancements, more specifications have been added for the fabric feature. The first one is global integrated memory. It's used for enabling remote DMA and messaging across domains via CXL fabrics. And the next one is dynamic routing. Message transfer can use different paths between source and destination ports dynamically. I suppose personally it seems a bit similar to the IP routing of TCP/IP. It is determined by congestion avoidance and traffic distribution across multiple links or link connectivity changes. And next one is security enhancement. So far, CXL has supported CXL integrity and data encryption, CXL IDE feature. In addition, CXL 3.1 also supports confidential computing. So CXL TSP is defined. TSP means Trusted Execution Environment Security Protocol. It defines mechanism for allowing VM guests to execute within a trusted boundary on direct attached CXL memory. Okay, next section is the status of current Linux for CXL. Summary of current status is here. Basic implementation of CXL memory driver and commands has been developed. The driver can detect CXL memory devices, and you can configure memory region interleave by CXL command. The repository of CXL command is same with ND control, which is the command for persistent memory. And a solution for the memory tiering issue was developed. CXL memory makes an environment which is called as memory tiering due to variety of access latency. Since Linux memory management system did not consider it, new feature was developed. There are some difficult issues for CXL memory hot plug memory pool feature yet. Even CXL allows device hot plug feature as a hardware specification, Linux has some issues for CXL memory hot plug. Today, I'll talk about the latter two topics. The first one is memory tiering. CXL memory has a difference of access latency compared to DDR memory. CXL persistent memory will be slower than CXL DRAM memory, and access over CXL switch is slower than direct accessing. As a result, memory access latency becomes tiering. The nearest DRAM from CPU, DRAM on another node, CXL DRAM and CXL PMU, and CXL DRAM over CXL switch. For this problem, CXL memory region is treated as a CPU-less NUMA node. Since Linux NUMA implementation considers for difference of memory latency, it's also suitable for CXL memory. There is no CPUs in the CXL memory device, so the NUMA node of CXL memory becomes CPU-less. In past, Linux memory management system did not have enough consideration for CPU-less NUMA node. Currently, Linux NUMA balancing policy is to use nearest memory from CPUs. It allocates memory on the same node with the CPU which process execute if possible. If auto NUMA balancing is on, contents of memory area on a far node are moved to node where the process is running. Since a CXL memory node does not have CPUs, process cannot execute on the CXL memory node. As a result, CXL memory may not be utilized as expected even if NUMA balancing is used. So Intel developed a new feature to solve this problem. Its name is demotion and promotion. Instead of swap out and swap in, kernel migrates cold page to CPU-less node, its demotion, and it migrates hot page to nearest NUMA node from CPUs, its promotion. So far, when a page is swapped out, CPUs cannot access its data until swap in. However, even if a page is demoted, CPUs can still access it. It's difference of swap out. Kernel decides which pages should be demoted in the page reclaim procedure. When a page is accessed by threshold type, kernel promotes it. The default threshold is 1 second, but the kernel automatically adjusts it based on the amount of promotion candidates and its bandwidth. This first work was completed in kernel 6.1 once. In addition, the community continues to enhance the algorithms for selecting the demotion target. So far, kernel has only used old specifications, which provides only ratios against the nearest memory latency. Since ACPI HMAT can provide detailable performance data, they are developed to use it. And CXL has also more effective performance information by CDAT. It may be used for it in the future. Okay, next is issue of memory hot plug, memory pool. CXL memory hot remove memory pool has 3 big issues. The first one is more software components are necessary for memory pool. And next one is the CXL specification itself causes difficulty in hot removing a CXL memory device. Not only specification, but there are many obstacles for memory hot remove in Linux. Unfortunately, I have not enough time to talk all of them today. So I'll talk about the last issue. What is the obstacle for memory hot remove? Please check appendix of my presentation about the other issues. You can, I'll update after this presentation. My presentation will be uploaded to speaker deck, and also schedule.org has already it already has my presentation, and you can see it. In addition, I'd like to recommend that you read my discussion at the community mailing list if you have more concern about these issues. To tackle the problem, I need to introduce how memory migration works. To remove memory dynamically, contents of removing memory must be migrated to another place. Kernel moves the contents of migration from removing memory to another memory without changing a virtual address. This is memory migration. Basically, this can work for user process memory, but it cannot work for memory used by the kernel or drivers, because its virtual address must be changed when the physical address is changed. Unfortunately, even if the memory is used by the user process, there are cases that memory migrate cannot work. You cannot hot remove such area. So long-term pin pages are one of the big obstacles of memory migration. RDMA feature like InfiniBand pins pages of users processing to transfer data from the pages without mediation by kernel. Kernel cannot migrate pinned pages because they may be under data transfer by the device. I guess the DPDK or any fast performance devices features may have same problems. And such kind of feature will increase. And VM guest also tends to pin pages to skip kernel or hypervisor for performance improvement. I think there is an ambivalent requirements like the following. There are many things which want to pin pages and skip kernel to make better performance. But kernel has the responsibility of any resources management in OS, and memory hot plug is one of them. The difficulty of improving CPU performance causes increasing the left side the requirements. Though kernel needs to manage total balance of system, it cannot be achieved by bypassing it. So I believe the root cause is lack of communication between such feature and Linux kernel. Current solution of Linux is here. Before pinning the memory areas on removable memory, the kernel migrates contents of the areas to unmovable memory like DDR memory. The current kernel can create zone movable areas based on user's configuration. Zone movable was created to ensure that removable memory is not used by the kernel and drivers. Therefore, it's beneficial for the CXL memory pool to allow hot remove. To configure zone movable, please refer the kernel documentation in the source code. If a for long-term flag is specified for the area the data transfer target, the Linux kernel migrates them for zone movable to another suitable place before pinning pages and data transfer. This is a reasonable solution for now. but it may not be the final solution. If the amount of DDR memory is relatively too small compared to CXL memory, it may not be enough for pinning areas. And VM guests also tend to pin pages of hypervisor. If a large number of VM guests are executed, CXL memory may not be effective due to DDR memory shortage. So CXL specification provides new approach. It's called a dynamic capacity device. It's introduced in CXL 3.0 specification. It allows that you can gather removable small memory blocks until required capacity rather than trying to remove stacked memory blocks. Then they can be transferred to another host. Memory pool will be available by this specification. However, I suppose it may cause other problems. A CXL memory device will have a mixture of following memory blocks: removable memory, unremovable memory, used by another host, interleaved with other memory devices, and shared by other hosts. Its management will be very difficult. In addition, replacing of the device may be difficult. So I worry about it. So one of my ideas for future is here. On-demand paging may solve this issue. ODP is a way a device can transfer data by RDMA without pinning pages. It's communicating between a device and a Linux kernel. When a kernel is going to invalidate a page for swap out or memory migration, it can notify the event to the driver and the device. When the device needs to access the invalidated page again, hardware asks the driver to execute procedure like page fault and can restart the data transfer. Currently, only NVIDIA network card support it yet. However, I hope more hardware vendors will support it. To understand ODP, I recommend the following. The Mellanox presentation and their paper are very helpful to understand ODP. And since we are developing an ODP support path set for software key, you can check and try it without any special hardware. Anyway, here is the conclusion. I talked about CXL specification overview and talked about the new specification of CXL 3.0 and 3.1 and current status of Linux kernel development community. I hope that many vendors will release CXL devices and boost the market. I also hope that many people will develop future drivers for CXL in Linux community. Thank you very much. Okay.
Have you done any benchmarking with the current NVIDIA product yet?
Currently, we don't have benchmark we can provide in public place. Internally, we've estimated how much performance is executed in CXL memory. Currently, it's emulation. Okay. Thank you very much. Oh, one more? Okay.
Okay, thank you for your detailed explanation. Could you go to the slide showing the new features of CX 3.1? Okay, in this slide, CX 3.1 support DMA and messaging across domains via CX Fabric. I'd like to know what domain means in this context, and also the use case of this new feature?
Okay. In CXL specification, domains means often says it's servers. So you can understand domains means servers. So global integrated memory provide the future servers across RDMA via CXL fabrics. Is it?
Okay. So RDMA over a CXL fabric is one use case.
Yeah.
In new. Okay. Thank you.
Okay. Thank you very much.
Okay. 皆さん、こんにちは。私はユウです。Hello. Good afternoon. I'm Shangxi. And this is the first time I'm representing my company speaking internationally. So if you cannot tell, I'm very nervous right now. But let's begin. So my name is Shangxi, and I work at SUSE under the Hardware Enablement Taipei Taiwan team. And I mainly work on BPF, but that's not the topic of the talk today. Today I'm going to talk about a brief walkthrough of how to work with OSS fuzz reported issues, and also a bit about how to submit patch to the Linux kernel mailing list, LKML for short. But my main focus today will really be the OSS fuzz report issue. So let's dig into it. The journey begins here. And at SUSE, we have a dedicated security team. They will monitor and track security issue for us. So it was a normal hot and sunny Monday, because it was always hot and sunny at where I live, and that's why I'm wearing this. And anyway, so I got a report from the SUSE security team saying there's an issue with the BPF. I'm the package maintainer, so therefore I have to look into it. And they forward me the CVE number, and so I can look into it. The first thing I check out is the CVE description. That's here. And it says that libbpf version 0.6 has some buffer overflow in the BPF object open function. That is quite specific, but not enough for me to fix the issue. So I keep on looking. There's this reference section in the CVE report. So I followed that link, and this brings me to somewhere else. So I could see that there's some information that I already know, but also some more new information that I don't yet understand, and also a few links to this website called OSS fuzz. So that brings a question. What is OSS fuzz? Looking into the documentation, it says that it's a free service that runs Fuzzer for open source project. And it's a service that was started by Google back in 2016, and later it's done in collaboration with the Open Security Foundation, which is OpenSSF for short. Now, all that is good, but the problem is that I do not know what Fuzzer is at that point. So I had to look into it. So what are Fuzzers? Well, I find that instead of saying what they are, it's easier to describe them by asking, like, what problem are they trying to solve? And the problem that they're trying to solve is around bugs. If you think about it, to fix bug, there's actually two parts of the equation. First, the bug has to be discovered, and only then can the bug be fixed. So this raises the question. Can the bug be discovered before the user, before the developer, or even the security researcher sees it? And basically, can the bug be discovered with minimum human involvement? And as you have guessed, the answer is yes, and Fuzzer is one way of doing so. And briefly, the Fuzzer works like this. So Fuzzer is a piece of software that feeds random input into a target. The target in my case is libbpf. And when it feeds this random piece of input, it also checks for unexpected behaviors. For example, program crashing will be an unexpected behavior. And when such things happen, it's a bug. And we have found one. So that's basically how it works. And knowing how Fuzzer works and knowing what a Fuzzer is, we can look back at OSS fuzz. So it's a free service that runs Fuzzer. In other words, it's a free service that tries to find bugs in open source software. And actually, it focused more on the security issue of open source software. So back to this OSS fuzz report. Well, I know now that this is a bug report, of course, but secondly, I also know that this is actually a bug report that is filed by software. So unlike your usual bug report filed by user, where you can interact with them and ask for more input and ask more questions. We don't get that benefit in this specific issue. But that said, OSS Fuzz actually provide us with a lot of helpful tools to debug this issue. But to get into the details, we really had to get our hands dirty. And the first thing is that I want to see the issue for myself. With that, I can kind of get into more details. And OSS Fuzz helps me by providing a reproducer test case. So what is reproducer? Well, back to our introduction of fuzzer. Fuzzer feeds random input into a target and waits for a bug to happen. Well, this random piece of input is the reproducer for such bug, which means that if I run this reproducer provided by OSS Fuzz, I should see the same issue again. The first thing is that I first need to to run the reproducer, I have to first set up the environment. And it's actually quite trivial. So the first thing to do is clone OSS Fuzz. And the next thing is to run OSS Fuzz provided helper to build the image. Here I have to provide a project name, which is, of course, libbpf. And this will try to get some container image, which could take a while depending on your network speed. It may take 10 to 30 minutes. And this build a container image for building libbpf. So it only creates this container image without libbpf yet. It's just the build environment. So the next thing I had to do is clone libbpf. And with that done, I can now finally build libbpf itself with the fuzzer. But for that, I have to give it 3 arguments. First is, of course, the project name, libbpf, and then the source to libbpf. And lastly, the sanitizer. So what is sanitizer? Again, referring back to our fuzzer introduction, we have some check for unexpected behaviors. And the sanitizer actually are the checks. So since there's quite a bit of unexpected behavior, different type of them, we also have different type of sanitizers. For example, for uninitialized memory use, we have the memory sanitizer to detect them. And for the shift out of bound, there's the undefined sanitizer. But for overflow, we use the address sanitizer. And there's also one for data race, which is the threat sanitizer. So you don't really need to know all this because OSS Fuzz report actually tells you that. In our case, we're using the address sanitizers, so that's what I use. And with that, it builds libbpf alongside the fuzzer. Now we have completed the environment setup, basically just 4 steps, and I can move on to running the reproducers. For that, I just download the link provided in the report, rename it just to make it easier. And then again, using this OSS Fuzz helper script, I gave it the reproduce command. And libbpf is the project name again. Reproducer path will be the one that I just downloaded. And there's also a fuzz target name. So fuzz target is basically what interface or what function the fuzzer is testing. And again, this can be seen in the report. We'll be using the BPF object fuzzer in this case. And actually, libbpf only have one fuzz target, so it's always this one. And we put that into the argument. And now I can start to see something. So there's this address sanitizer report saying there's a heap buffer overflow. So if you think about it, it's just like 6 steps going from knowing nothing to reproducing the issue locally on your machine. So I'd say that's a very nice thing to have. And with the issue reproduced, the next thing is to try to diagnose what's wrong. And the sanitizer and OSS fuzz actually helps you a lot with it. The sanitizer report contains a lot of information. The first thing it contains is exactly at which function and which line of source code does the issue happen. So we can see that it's here. But this heap buffer overflow issue actually requires more digging. You need to know the root cause by looking at where it is allocated. And for that, you look at the second part of the address sanitizer report. And I can see that it's occurs in the same function, just a bit higher up. So I can tell that while the heap buffer flow happens here, the memory was actually allocated here using some section count. And I can tell that the section count comes from elsewhere, from another field. So this is a point that it started to get too specific into the issue itself. So for the next part, I'll kind of just skim through, and mainly for time constraint and not digging too much into detail. But in short, with just printf magic, I realized this number is 0. And looking into the spec, there's a part of the ELF spec saying that such a number can be 0, and in such case, the real value is stored elsewhere. So I have to look somewhere else. And just so happened that I could use some helper functions for it. So I could use this elf get section header number and to retrieve the real number that I'm looking for. So I apply the change. And next thing I want to do is to see if the reproducer still could trigger the issue. So I had to rebuild the fuzzers again, rebuild libbpf, because it's compiled and I changed the code. So compiled it, and the next thing is to try to reproduce again. So this time I see that no address sanitizer report came out, which means I have fixed the issue. So all is great. So next thing is just to commit. And that concludes the first part of my talk. The first part about how to use OSS fuzz. I hope it's clear enough that it's quite easy to use, and you can surely, well, not surely, but most of the time, you should be able to find the OSS fuzz report and reproduce the issue locally on your machine. And now move on to the second part, submitting a fix. So if you just ask a random project, like where should I submit the changes, you can say GitHub, and you'll be right like 90% of the time, but not for libbpf. So although libbpf has a repo on GitHub, the changes should be submitted to the BPF mailing list, because libbpf is integrated into the Linux kernel source code. And for that, we have to post our patch to the BPF mailing list. So it's not really LKML, like the topic kind of, the subject of this talk is kind of off, but please forgive me. I think the process is close enough, so what I'm going to say next should apply to LKML as well. So, posting patch to the BPF mailing list. So if you have not worked with mailing lists before, or you just heard of it for the first time, it's essentially a discussion forum, kind of like Stack Overflow and like Reddit, except all the exchanges are done through emails. And there's quite some specific requirement for sending emails, especially sending patches there. The first and foremost, the most important part, I would say, is the email subject, because that's what everybody sees at the first sight. And the email subject actually contains two parts. The first part, enclosed in the square bracket, is a prefix. inside the prefix, you have to specify that I'm sending a patch by saying patch. And secondly, you have to specify what tree this patch should go into. So tree is essentially just what repo that your patch should go into. For that, you can look into the BPF mailing list developer guide, and it tells you that there's actually 2 BPF kernel trees. The first is BPF, the second is BPF next. Now, since I'm sending a fix, I see that BPF tree itself is for fix. That's where I'll send. So I use BPF for the tree. Up next is the version. So what version of the patch set are you sending? So this is the first time I'm sending this patch. So version 1. And for version 1, you actually can just skip it. So that's fine. Now we move on to the last part of the prefix, the sequence number. This is mainly for a situation where you're sending multiple patches at once. And in my case, in this simplified case, I'm only sending 1 patch. So 1/1, I can also skip that. This leaves me with the prefix of patch BPF. And up next is the component part. So for component, I find the easiest way to find it out is just to look at the git log and put in your file and see what other says the component it is. So in this case, it's pretty clear it's just libBPF. And that's what I use. So last and probably the most important part is the actual subject that you'll be using. And I find that it's really hard to come up with a good subject like just right away. So what I do is I actually skip this part and postpone it until later. So I'll move on by generating a patch. Well, actually the email file that I'll send for my patch. This can be done with the git format patch. And recall that we already have a prefix that will be used in our emails. So I gave it to this command with the subject prefix. And I also specify which commit it should output. Since I'm using the last commit, I'll just use head -1. And this will give me an email file that I could further edit. Fire up the editor. And this is likely what you'll see. So what I need to do next is to fill it up with some commit message. And I find that usually when sending patch to BPF mailing list or LKML, I find it's pretty nice to have some template. And the template that I'm using is basically abstract, followed by content, followed by summary. So abstract is just very short sentence saying what this does and why I did this. The content will go into a bit more detail on the reasoning behind this change, and followed by the summary that encloses everything. Since it is a fix, I usually get into more specific details. So I would say what the symptom of the issue is, and followed by the root cause. And so for my patch, in this case, this is what I'll say. For the abstract, I look at what my changes. So I replace a field with a helper call. So that's what I'll say. I say this commit replace this field with this helper call. And as to the why, well, because I want to fix a heap buffer flow issue. So that's it. Now I can move on to the symptom. For the symptom and for OSS fuzz, I actually have a very good summary. And that is the sanitizer report. Paste it in, and the maintainer usually will have a pretty good idea of what's going on. And for the root cause, I use the ELF spec content a bit summarized and reduced, but that makes a pretty good root cause discovery. And for the summary, I just go over the reason again, followed by the changes I made. And now I can go back to fill the title. So the subject is, firstly, it has to have the component, so I add it. but I also need the main part. And I find that it's usually pretty easy to extract something for the first part, the abstract of my commit message, and just stick it there. So in this case, I decided to say, this just replace some field with the helper function code. Equally, I think I could also say that this commit fixed a heap buffer flow issue, but that felt a bit too general. So in this case, I thought it's better to be more specific and say my changes. Now we're almost done. You have to still add some more things. So first is the certificate of origin. So any patch you send to LKML, the kernel source code, must come with a certificate of origin. Secondly, it would be nice to say that what this patch fixed. So the main use for this is like distro maintainers like me or others can discover that, oh, there's some issue with the code base I'm releasing and apply this fix to some older release product. And it really helps with the whole process. And thirdly, if you have some link to some external reference, like this case, it would be nice to add it. And I had to do a bit of trick to make it work, but if I had the time, I'll talk a bit more about this. So up next, before sending email, you also have to configure your Git config to properly send the email. And my configuration, my setup is basically msmtp plus mute OAuth2 script. And with that setup, I can actually send all the patches through Outlook. So if my setup could work with Microsoft, it probably could work with any setup out there. So it should be worth trying. And with that, I can send out the email with the send email command as the name implied. So you have to send it somewhere, which is the BPF mailing list. And it's also nice to have a dry run to test your script, test this, whether it works before actually sending out. So once you make sure that everything works nicely, you can actually send out the message. And to be very complete, this would be the command line I would actually use. So the one on top actually just send to the BPF mailing list. But ideally, you want to send also to the maintainers, not just the list. So just to make sure they get it and they see it. So for completeness, this will be the one I'm actually using. But I think if it's like a very simple fix and just one shot, I think nobody will shout at you by sending just to the BPF mailing list. And after your mail is sent, it start a code review. In my case, the libbpf maintainer says that there's something that bothers him with the code I have, and he suggests some fix that I should do. So I does the change. I make the use of helper function closer to the actual allocation as suggested, and commit, amend, format patch. This time it's the second time I'm sending my patch. So I had to add version 2 and also slightly added the patch. So when you're sending another version of your patch, you need to specify what changes are made. And usually this is done in something called the cover letter. So when you're sending multiple patch, you'll send the first kind of like a summary of what your whole patch set does. But since I'm only sending a single patch, in this case, I'll put my changes just before the stats of the diff. And this way, I have something that the emails reader would see, but it also would not make it into the final Git repo. And so I say that the changes I made, I actually go against a different tree, and here's are the changes I've made. And then send it. So that's pretty much I guess the end-to-end process of going from finding an OSS first issue into having your patch accepted at the Linux kernel source. And if you're interested, I think there's a lot of opportunity for contributing mainly against OSS fuzz, but of course also against Linux kernel. But the slide will be mainly about OSS fuzz. So OSS fuzz actually tried to build and fuzz a lot of different targets. And right now there's actually quite a bit of targets that are failed to build, which means they're not getting fuzzed. So if you want to help, you can look into that. And there's also a tracker for all the OSS fuzz reported issue. That's also something you can work in. And there's some more resources, mainly on fuzzer and on sanitizers. And that would mark the end of my, I guess, the main talk. So yeah, arigatou gozaimasu. Thank you. So any feedback or questions?
This is just some feedback. I work on the team that supports open source fuzz, OSS fuzz. There is money that Google will give you if you help improve OSS fuzz. So check out the Bug Hunters page at Google and you can learn more there. Yeah.
Yeah, thank you for that. I forgot to mention. Yeah, I think there's some, as mentioned, there's some bounty. Let's see if I can open. So you really get paid, I think, quite a good sum of money if you try to integrate it into the existing open source project. The first one, right? Yep. So is there some like threshold or some requirements for the open source project to be considered part of the award program?
It's on the page. So it will get checked for the criticality of the project. So like just picking some random project no one uses won't get a bounty, but you can get up to $5,000 for really critical projects.
All right, thanks.
I'll also add, like, this is also includes, if you scroll down, improving coverage as well, which is, yeah.
Yeah, so one thing I think I learned while looking at fuzzer is that besides issues like crashes or memory sanitizing issues, fuzzer could also be used to find some logical errors, I believe. So I think one thing that math-related library could be fuzz is that if you have two implementation of the same library, and you could try to give them the same input, and if they give you different result, that means something is wrong, and this is a logical issue that someone should look into. All right, so I guess that sums up my talk. So If you don't remember anything, just remember that you can get paid by integrating OSS Fuzz into important open source project. And thank you, everyone.
始めていいですか？はい。So, hello everyone. Thanks for coming. So I'm Daiki. I'll be talking about a bit of cryptography today. So before starting, let me briefly introduce myself. I'm Daiki Ueno. I'm a software engineer at Red Hat. I mainly work on low-level crypto packages in Red Hat Enterprise Linux. So we call it RHEL. And as a fun fact, I lived in Czech Republic for the past 6 years and returned to Japan only last year. So this talk is about our new project called crypto auditing. So it is a tool to monitor cryptographic operations performed on a system. So why we are doing this? So a basic assumption is that cryptography is used everywhere for protecting network traffic, for encrypting disks, for signing packages or containers. So for example, if you just access a random website, you will be typically using HTTPS. That means your connection will be encrypted using TLS, and the server's identity will be verified using PKI and digital signature. So, yeah, so regardless of whether you like or not, you will have to use a cryptographic algorithm every day. But the problem is that the underlying cryptographic algorithm has its own lifetime. So I put a couple of examples here. Triple Des, MD5, SHA-1, RSA with small key sizes. These are considered deprecated or even broken. So also, in the next 10 years, it is said that quantum computers will be a real thing. It will easily compromise classical public key algorithms. So there will be more to come to deprecate. And yeah, if you keep these legacy algorithms on your system, that could mean that your system will be eventually vulnerable. So let's look at a couple of examples. The first one is SHA-1. Maybe everyone knows it, but it's a secure hash algorithm. It's commonly used for digital signatures. So for traditional digital signature scheme with RSA or ECDSA, it does some hashing before applying the asymmetric crypto. So if a collision can be easily created, that means the digital signature is meaningless because the attacker can create a very rigid signature from arbitrary text. So 2017, there was the first collision attack was proposed, and 3 years later, there was a much more efficient attack was proposed. So at that time, only $45,000 was needed to just create a collision. So a second example is RSA encryption with PKSS1 padding. So this scheme is still not vulnerable, but it is very hard to use correctly or securely. So if you misuse it, it will create some timing side channels that would leak plain text to the attacker. So first of this kind of attack was proposed in 90s by Brian Baher. And there were a couple of more variants was proposed recently. The first one is Robot in 2018, and next one is Marvin, discovered this year. So quite a few number of CVE were assigned for these attacks. So last example is triple handshake attack. TLS, transport layer security, uses temporary session key to encrypt the traffic. So, but the original TLS 1.2 key derivation process doesn't take into account of the handshake transcript. So that means the man-in-the-middle attacker can intercept the handshake transcript and can impersonate as a client. So there was a mitigation proposed in RFC 7627, that is to use the extended master secret extension to generate the key. So it basically binds the handshake transcript to the key derivation. So, okay, so after looking at these examples, I guess most of the people agree that the best practice would be to regularly review your system configuration and tighten the cryptographic algorithms being used on the system. But this process is not so easy, especially for system administrators. They need to be familiar with cryptography and need to follow the recent researches on that. So we created a tool that's called Crypto Policies. So this is a tool to provide a system-wide baseline of the cryptographic algorithms. So it's already adopted in Fedora, Rail, and OpenSUSE. So this is a good tool, but there is one problem, that if you change the default, there will be likely some pushback from the community, because if you suddenly disable working algorithm, it's not completely broken, and there are some users, they will be upset. So yeah, we went through this process for 3 times, and the latest one is still rejected. So we need a way to identify the actual usage of cryptographic algorithm on the system. So now, with the help of crypto policies, we can tighten the configuration to use the latest set of cryptographic algorithms. So the question is this sufficient? Actually, no, because the implementations also matter. So Red Hat Enterprise Linux include FIPS certified cryptographic modules. So they are they pass the code review by the separate laboratory and pass the acceptance tests. And also we implement additional requirements like documentation or necessary API. So yeah, that means as long as we use these certified module, we say it's kind of secure. But something could happen. So this was a CVE discovered this year. So we ship dual stack crypto backend in Go applications. If the system is not in the FIPS mode, we use the cryptographic code written in Golang. It is not certified because the code will be copied to everywhere when linking. Instead, in the FIPS mode, we use DL open to delegate all the cryptographic operation to the system library. So, but for some reason, this switching was not working, and that means the non-certified implementation was used in FIPS mode. It is already fixed, but we need a way to prevent this kind of issue. So we need a tool for 2 purposes. One is to help tighten algorithm selection, and the other to ensure the correct implementation is being used on the system. The first purpose is can be done with crypto policies, but this means kind of long-term trend analysis. Like 1 year or 2 years, there will be no user. We can safely disable some algorithms. But the other purpose, to ensure the correct implementation is used, we need more real-time auditing mechanism that indicate which implementation is used when you do some operation that would use cryptographic operations underneath. So that's the introduction. So let's go into the details of this tool we propose. So first one is the goal, that we are trying to create an infrastructure to monitor all the cryptographic operations happening on the system. So we want to support all the FIPS certified modules. We also want to support long-term and real-time auditing process. So second one is challenges. There are always challenges for this kind of infrastructure. So crypto auditing shouldn't degrade system performance as a whole. Secondly, privacy is also a concern that we can certainly collect any information from the user, but we shouldn't actively do that. And lastly, maintainability. So what information will be collected, maintained as a rule? So this kind of rules will be larger and larger as this project evolves. So we need to make a way. We need to provide a way to ensure maintenance is easy. So here is the architecture. So we propose the core component is the agent. This agent installs eBPF program into the kernel, and the kernel attaches it to running process to receive the cryptographic operation is happening. So after receiving the event, it sends back the event to the agent, and the agent writes the events into a file in an asynchronous way through IOU link. And this log file is just a normal regular file. So it can be read as normally, but we also provide an event broker service that periodically polls that file and distribute events to real-time auditor clients. So next thing is logging mechanism. So we decided to use eBPF to trace the user space programs when the cryptographic operation is used. So first, there are multiple ways to do that. One is uproofs and the other is USDT. We first tried to use uproofs, but found out that it's not suitable for this purpose because it can only monitor enter and exit of function calls. So why it doesn't work? Let's look at the OpenSSL signature API. So just to create a single signature, we need to call 5 functions. So if we track all of them, the tracking process will be quite heavy and complicated. On the other hand, if we use USDT, user statically defined trace point, we can put arbitrary trace point to any binary. Yeah, it's brings us a lot of flexibility, but the problem is that we need to somehow maintain the proof points by ourselves and hopefully upstream this proof points implementation to the projects. So let's look at the file format. So our file format is quite simple C4 format, but in higher level, it is organized as a hierarchical manner. So for example, this indicates a TLS client handshake, and it takes some time, and during that period, there is some certificate verification event, and there is one event, RSA size 3000 kilobit RSA key is used. So this kind of tree is represented in the file format. So we define 2 kinds of elements in this format. One is context. Context defines the period of time where events or other context can occur. And context can be identified with 16 bytes unique ID. For privacy reasons, it's obfuscated by the agent when writing. It's also associated with a name. In this example, TLS handshake client is the context, and it's assigned with this name. And the event is just a moment of time. So, yeah. So this PKRSS size is an event. It's kind of single key value pair as an event. So these can be encoded using 4 primitives we introduce. Context introduction, we use new context, and we support only 3 event data types: integer, string, or arbitrary sized blob. So let's look at the example. So this is TLS handshake client with a couple of events added from the previous example. So gray rectangles are context. So the root context is handshake client. It has 2 children. One is protocol version event. The other is certificate verify context. And TLS certificate verify context has 2 children. One is signature algorithm, and the other is RSA size. So if we just write down these events into a file, it will be too insufficient for disk space. So we also added some basic compression and also log rotation mechanism based on the context ID and time window. Yeah, we are not going into the detail. So yeah, we have plenty of time, so we can do some demo. So we'll cover 3 scenarios. So first we will do basic operation, and secondly we do visualizing logs, and thirdly we can spot actual problems. So the basic operation is quite simple. You can just access the log with the crypto auditing client. It will connect to the event broker and receives the event and write it down. And afterwards, you can parse the log with this log parser program. So let's see. Sorry, I'm not feeling lucky today, so I'm using the recording. So now we use JSON as the output. So if you access the fedoraproject.org by HTTPS, you receive the events real time. So now we can store the events into the binary file. So we use cPower and storing it to this file. And we do the same. And call the log parser. So as you see, there is spans, context and spans. Spans contains the children. So it's basically passed back into the tree. And there's an interesting thing. There's origin value. It's hexadecimal value. That means it matches the build ID of the actual shared library used. So wget is using GNU-TLS. So libgnu-TLS build ID is embedded in the event itself. And you can also visualize this event as a frame graph. So yeah, we include this script for post-processing. So now take a look at our legacy key derivation process. So we access fedoraproject.org after disabling TLS 1.2. And then we can access this badssl.com, which we know that it doesn't support extended master secret. Now the 2 handshakes are recorded. And let's look at the frame graph again. We have 2 handshakes. One has extended master secret here. But the other doesn't have. So this kind of problems can be easily detected with this tool. Yeah. Okay. So let's move back. Actually, we have a way to produce the SQLite file that can be easily imported to Grafana for further analysis. We did this. Let's look at the implementation. So this project is hosted on GitHub under the Ratchet organization. It is written in Rust, and they are available on Crates.io now. But we recommend using RPM packages because it includes the specific version of it is compiled against the specific version of kernel. So we provide a couple of RPM repositories. One is for the Rust component themselves, and the other is instrumented crypto libraries. There are only on OpenSSL and GNU-TLS are there. So afterwards we measured some performance to ensure that this tool doesn't degrade the system performance as a whole. So we created a simple program that just performs TLS 1.3 handshake 10,000 times. It only uses memory-based transport, so it doesn't do any I/O. And it is interesting to check the performance on single-core and multi-core systems because BPF program usually involves some context switches. So if any available core, it can be utilized. So we use this command line, and here is the result. First table is the overall time spent. It's in seconds. So in the single core case, there are a bit of degradation that is 4%. And but on 8-core systems, there is nothing or little to no difference. But looking at the context switches, the difference is quite significant. It's almost 7 times more. But we expect that that's because we are not doing any I/O. So if we deploy it on a practical environment, the difference will be much smaller. Yeah. So future work. So first thing is the instrumentation. This work is still ongoing. Yeah. We talked with OpenSSL upstream, and they basically agree with this approach. And I'm the GNU-TLS developer, so I can push for community adoption. And there are also NSS, libgcrypt kernel. So we need to think about how to figure out kernel crypto usage as well. As I mentioned, as I briefly mentioned, that there is a Golang Golang-based cryptographic code. They are usually statically linked to each application, so it is quite hard to track the usage. So we need to probably figure out how to monitor. Maybe a different mechanism would be needed. Yeah. So for the miscellaneous stuff, we already support the batch analysis of frame graph using Grafana, but it will be useful if we create a real-time analysis plugin for Grafana. We also should support applications inside a container. Yeah, so basically this is the last slide. The conclusion is that cryptography is a tool to identify cryptographic operations happening on a system, and it supports long-term and real-time analysis. The architecture is designed to be fast and simple while preserving the privacy. So, any questions or comments?
Thank you. So you mentioned that future work includes instrumenting applications that are running inside containers. How do you plan to do that? Doesn't that also require that the USDT instrumented libraries happen to be in those container images that you want to instrument?
I would expect some namespacing at least needed to collect that information as well as USDT proofs. So yeah, I haven't think about it much.
Right, but because USDT basically requires you to modify the libraries themselves, that means that the supply chains for building your containers need to also support this.
Yes, so we assume that all the crypto component in the container will be instrumented as well.
All right, thank you.
We have some production services running on Debian and Arc. So how do you suggest that we can use this together, let's say on a Debian service? Because this is only running for, I think, Fedora or Red Hat, is it?
Yeah.
And I was just reading your package. I think it's only released for Fedora. So let's say if we have some services hosted on some other distro, so how can we use this together? Can this run as an agent or?
So the USDT proofs are designed to be quite generic. So if the other distributions are using the similar proof points, we can collect the same information. But yeah, we probably should provide some central repository of what would be the event we can process. So, yeah. Did you say about some VPN? No? Okay. Okay, good. Any other questions? Yeah, if not, we can end the presentation, and yeah, I'll be at the sponsor stand, so yeah, let's talk. Thank you.
私はあ、本当も見える。両方。
Please look at those instructions.
はいはい。I have to look to these instructions. So 英語で I got in English instruction. 難しいね。うん。さっきもなんかずっと日本語喋って、英語なんか、日本語喋らないと日本語喋る。はいはいはいはい。でも本当に私の時間になる。あ、そうなの。うん。自分自身見てないの？知らない。顔パレする1ではなく合ってる？ああ。今コーヒーブレイク中だから。あ、コーヒーブレイク中。まあまあまあまあ。ちょっとスライド見ててよかった。アルコール飲みますか？ビール飲む。なんで1個1枚増えてるの？おかしくない？そうそう。ドラえもんのポケットだから。ああ。いやいやいや、私。うん。ラストどこにもないけどな。うん。
は。
採用
とデビュー。これは
わし
一応スピーカーの方へのガイド。
はいはい。
まあこれ出すのと、
はい、
あとは質問があるときは、
はいはいはいはい、
なるべくリピートしてく
はい
ださい。なぜかっていうとマイクで
あー
喋んない人がいるので聞こえないから、
はい
っていう録音が取れない時がある。
わかりました。
で、あとは時間と、
はいはいはいはい。
レザーボイド。
わかりました。まあもしこう多分早めに終わるかもしれないし、ね、3分ぐらい40その質問に入れると何分ぐらいがちょうどいい？
ちょうどいいのは、このセッション40分なので、そうね、30分ぐらい話して10分ぐらい Q&A やっていただけると一番いい感じではないかな。
50、10分ぐらい。
それだと一番いい。
時間した。
お願いします。
準備してたよ。してました。I think we can start. Okay, hello everyone, and thanks for coming to my presentation. And the presentation is about Rust in kernel CI, but it's mainly about kernel CI. And Rust is a catchphrase. And yeah, but I will talk a bit about also kernel, about Rust. So I'm Harisu Tachibana, and I am a Gentoo developer, and I'm part of the kernel CI technical steering committee. I'm part of the CIP, and I work for Cybertrust Japan. So about this presentation, most of the things that I say, that is right in my presentation, are mostly my opinion. So yeah, mostly my opinion. So we talk about a bit about what is kernel CI and what is Rust for Linux, but I think that most of you know probably what is kernel CI, what is Rust for Linux. And then I will talk about what we are implementing in kernel CI for helping with testing with Rust for Linux. So kernel CI is a continuous integration system that is used by the Linux community, and is send some mail report to stable mailing list and to some practically sending to Greg. But everyone can see from the mailing list, can see the report of kernel CI, and yeah, kernel CI is trying to take a distributed approach. So every part is practically can be distributed theoretically. So kernel CI is done by the technical steering committee and advisory board. And we are meeting the technical steering committee is one at month, and I think also the advisory board, but I'm not sure because I'm only in the technical steering committee. And there are some members that are supporting work of kernel CI. So kernel CI is helping practically keeping what we, at least giving a view on what we are adding to the kernel, and see that nothing's broke. So why is it scalable? Because it's divided in, we are using different part of KNCI that can be installed, distributed. Lava Docker actually is still the main KNCI laboratory, but is currently we are trying to not only use Lava Docker, but also trying to use different system for having testing. And we have also some repository where we are adding the test definition. Okay. And we are using currently Jenkins, but we are moving to a different system that is called KNCI API, but is not completed yet. I think some part of it is working with that, but not yet everything. So we have not only KNCI, but also some other operating systems that are helping sending data to KNCI, and all this data is sent upstream, or anyway can view by KNCI website. So distributed, and yeah, we have many test lab, and everyone can add his own test lab. And we have current kernel 3 under that are tested by KNCI, but actually there are more, and I think I didn't add Rust. Yeah, I didn't add Rust. So Rust for Linux. Rust for Linux is the project that is trying to adding support to of Rust to the Linux kernel, and yeah, is made by I think Michael Ojeda, some other various maintainer and reviewer, and the work is supported by this company. And yeah, is adding the support, and if you want to use it, there is many guide online, like explaining how to use Rust for Linux. And what the current things of Rust for Linux is that is currently only support a specific version of Rust. And like you can try to probably build with old one, but probably not everything is working, because as explained after, Rust for Linux is using some unstable feature of Rust, and this can break when you try to use Rust for Linux. And then it's using bindgen that is binding the C side of the kernel, and CLab part of LLVM. So I think I already. So yeah, I was talking about the unstable feature that is using Rust for Linux, and actually there are many, and I don't know how I can show that page. There is a pending issue. Actually, I was thinking about making this recently I was thinking about making this more of a both presentation for everything that is. So this is the list of all the unstable feature that is using Rust for Linux. Needed for the kernel, and there are actually many. So, and that's why only one version of the Rust is practically working with transferring. And so currently Rust for Linux is using two main systems for checking every patch that is going to Rust for Linux. One way is using CNCI, and the other way is using GitHub Action. But I think GitHub Action is currently only for, like, they recently deprecated the Rust branch in favor of Rust Next. And I don't know if GitHub Action is yet working on the Rust Next. And CNCI recently deprecated the Rust branch. So we got added the 1 year ago. We got added the branch of Rust for Linux under CNCI for taking it under control. And from there, we in that patch, actually, we got the the branch repository, and then we got the fragment of the configuration that is going to build for in CNCI. And we enable the module, some sample module for checking that Rust for Linux is building, but the problem was that recently we are actually not building it, and I look at why, and probably we didn't get the first part of the fragment, but only the sample part. So I sent a pull request yesterday for asking to build both. And yeah, this one is the core practically of CNCI that is building Rust for Linux, and is also building KSF test, but I'm not sure on what reason. And the interesting part is the build environment, that is the environment that is used for building Rust for Linux. So CNCI is practically each build have its own environment, and Rust environment is using Clang, is based on Clang plus some Rust component. And so we are, I will show after, but we are making the Docker of Rust C, and actually anyone can use that. And this is the patch that I sent it actually yesterday. And we started to build some module, but yeah. Actually, I still have to think about what we have to do with such okay, it build, but what other tests can be done, and if such tests are enough good for CNCI. And so, yeah, the Docker, the first part of the building feature that we was making the Docker image is actually on anyone can download that and play with CNCI Docker image. So the Docker image is another fragment in CNCI. The first one was YAML, and this one I think is Jinja, because it's practically just the Docker compose part of the Docker building image. And we're trying to follow Rust for Linux. Rust for Linux is helping us. We're sending some patch like when we are stabilizing the new version of Rust, we are sending us usually the patch for the new Rust for adding new version of Rust C. So we are actually trying to collaborate also with Rust for Linux, and Rust for Linux is collaborating for us I sent also some little patch for Rust for Linux. So the Docker part is practically just getting the Rust toolchain, and with the Rust toolchain is just is installing the toolchain that we have. The Rust part is then worked by another part, and installing Binjan, and then I think is installing also Rust FNT, that is the formatting things of Rust. And then we have also Clippy, but we are not using Clippy, so it could be a new feature of what we want to test with kernel CI. There is on the kernel.org, there is in the documentation is right the minimal version for building with Rust for Linux in the kernel. And you can also do some, Rust is available for knowing if it's building or not. So I was saying recently we deprecated the Rust branch. So a new development branch in Rust for Linux, it became Rust Dev, but is not yet under kernel CI. The problem of putting everything under kernel CI is that we also need to see that we are not overflowing the resource of kernel CI. So now this one is how you can see from the web page about the build of Rust for Linux. And checking that we are building Rust. So in the kernel CI web page, there is, if you click on the build option, you can add write Rust in the search, and you will see all the build that we are doing for Rust. And currently, I think in the production version of kernel CI, we have probably really few build, and we are mostly building on the staging version, that is the development version of kernel CI. So yeah, I'm trying to move in such things to the production of kernel CI, and yeah, with author of kernel CI and Rust for Linux. And yeah, if you click on the result on the build status, you can see. But I think also by the mail that is sending each time. I don't know if staging is actually sending the mail. We will try to send the mail from now on. Yeah, I don't know how it's feasible. And yeah, if you see on the build, there is the log, and on the log you can see that actually building Rust, but this need to be automated, and this is not automated, I think. At least it just automated the fact that if nothing broke is okay, but and yeah, we have the Docker that build, and that is the node name, that is Rust 3, the last version, I think. So the future, so kernel CI is currently building Rust, but it have not so much of testing of Rust, some part, but like is using the sample configuration that is inside the Rust for Linux, first, that is building some module and say that is everything okay. But I think recently, and that's why we had two Rust samples, because actually they are both compiling the sample in Rust, but they are doing the same things, and actually I'm not even sure why we had both. And I think one of the sample part are not building, because I tried yesterday and I couldn't, I found only the print and some part of, it was a mix of Rust for Linux sample and Rust sample. So we probably have to fix such things. So another thing that we can use is using Clippy, that is the lintian of Rust in that is used by Rust for Linux, but not everything that Clippy found is actually a problem for Rust in kernel. So I tried to send some pull requests about that. Some got closed, some got merged. I think few of them got actually merged. And then recently, I don't know the pronunciation, Lowell introduced Cosinel for Rust at the last Rust for Linux workshop in 2 months ago. And we actually have a Cosinel Docker environment on kernel CI. So I don't even know if it's actually used by kernel CI or if we just have such things. So this could be an interesting part of making Cosinel check-in, also checking the Rust for Linux. So I don't know if someone is interested about looking into this. And then also this one, I think this one is more old, but I read about that also 2 months ago, that they recently could use Rust C code gen GCC for building Rust for Linux with GCC with this patch. And so we could also make a Docker for Rust C code gen GCC. So this could be another option. And other thing that was talking Ojeda-san on Rust for on one of the pull requests that sent to kernel CI was that we are currently following the maximum version, the one only version of Rust, but in the future he said that we will be also the minimum and maximum version. So probably kernel CI will follow both, but it's still about how many resources we can use for checking everything. I don't. So someone, me or some other person will try probably to send a patch for this in the future, but I don't know how much it will be near. Or probably the things that there has to be done before this, thinking about this, is probably about the unstable featuring that Rust for Linux is using on Rust. So the conclusion is not actually a conclusion. It's just fun with Rust for Linux and kernel CI. And I don't know if there is any. Also, this is why it probably was better to make a both and not a presentation. If there is any suggestion on any question, I don't know, anything about both kernel, well, probably more about kernel CI than Rust for Linux. If you have any question, anything, I can try to reply. Also, if it's not about Rust, if it's just about kernel CI for something. If there is nothing, I'm okay also. Yeah, but it's kind of say documentation. You have Rust for Linux documentation. So if you want,
I have a question.
Okay.
So
So anyone can add a test to kernel CI and.
Okay, I have to repeat.
Mike.
Okay. Yeah, KNCI is practically on GitHub, so anyone can send a pull request for KNCI. Probably it's also about if I send a pull request to KNCI, will that pull request be good for KNCI? Will be merged by KNCI? I think the best is anyway sending something. Also opening an issue and asking, is this feature good for you? And I'm not the only technical steering committee. We are, I don't know, I don't remember how many. We recently became less 2, so -2. So anyway, one of them will anyway reply, but I think it's good to see that there is some involvement in KNCI in any case. So if there is something that you want to change in KNCI, please send. The only things that I get a bit strange at myself is that currently we are trying to replace Jenkins with something else. So if there is a patch for Jenkins, probably, I don't know how much it will be accepted, such things, because, but if it's like, I want to add this tree, I want to change, or I want to do this test or that test, that I think you can anyway send and is more than welcome. Yeah, that is more
adding
than
tests
welcome.
to the kernel.
Yeah.
That's done through the same repository?
Yeah.
Okay.
That is more than welcome. And yeah, currently we are doing such things with Lava, so practically is some Lava, but also if you send like probably also a draft pull request, sending like I want to add this one and that one, and then someone will come out and tell you how to add like the Lava part or where to add. If you are interested about the test, there is the testing framework repository, I think, in KNCI. And you can see all the tests that is doing on Lava. And other part is Docker. We have the so one can be the test config. So you can go to the KNCI core config or test config, and there is all the configuration of the testing. And you can see where is getting such things. And probably if it's Jinja 2, is probably from Lava. And wait, if it's Jinja 2, it's just the yeah, it's probably from Lava. And yeah, this is the list of all the tests that are done. And another one is, I was telling you, this is the Docker part, where there is also the Rust and there is the Coccinelle one. But, yeah, somewhere in this various Cosinel and CVA hunt, and yeah, there are a bunch of things that are used for also for testing, not only for toolchain. Yeah. And the last one that I was saying was the framework. Test definition. That is all the lava test definition of that. Yeah. In any case, showing that there is some interest in some testing more than other testing is anyway good, I think, and showing that anyway there is interest in building such things. I don't know. I think Rust for Linux was at first introduced by KNSCI developer, I think, and then Rust for Linux community started to help keeping the Rust for Linux testing update. So recent from 1 year ago, almost after we got the first pull request, we started to get pull requests also from Rust for Linux community. Yeah, so showing that there is interest, I think, is good for showing that there is also such things in the community that could be a good tool for keeping a check on the tenor. There is also, I think, some people that is using also for development. There is, I think there is some branch that are just added like as development version. Not, yeah, so yeah, so there is also such possibility. I think one of the things that I try to say is that with the change from Jenkins to kernel API, would be nice probably to give such possibility by like some credential that is giving the possibility to send some code or something to KNSCI, and it will be such things. I don't know how much it will be implemented of it. Yeah, but probably my I am starting to divagate on the question. Yeah. If there is any other question, anything else?
Thanks for the presentation. And now I'm trying to access to the KCI-DB dashboard.
Oh, okay, okay.
But unfortunately, it says that the dashboard is temporarily out of service due to some resource shortage. So does it happen often, or?
I also see it yesterday when it was.
So maybe I can try next week. Can I see the dashboard working?
I think, yeah, you should talk to Nikolai about that. Nikolai is the guy of KNSCI that is working about KCI-DB.
I see. Anyway, so I'm very interested in it.
Oh,
okay, thank you very much.
So KCI-DB is giving out some credential to people that want to contribute tests on KNSCI. And so, as I was showing it, the presentation, one of the first presentation was like showing that there is KNSCI and then there is like Red Hat and Gentoo, and also some other that have their own testing system framework, but we want anyway to collaborate with KNSCI result. So usually the way is to add a new issue to KNSCI requesting a new credential for your framework, and we will give you your credential for sending your test to KCDB. And there is the command of KCDB that is made by Nikolai. So that part is mostly, I think, made by Nikolai. So. I also was, oh, it's down. Oh, it didn't work. Oh. Yeah, thank you. So, any other question about something that currently works?
Any other questions? Okay.
Okay, thank you. Thank you for coming. Yeah, I hope probably to make some advancement on these things and came in with something more interesting. See you. Thank you.
Okay. I guess we can start. Yeah, maybe one short second further. Okay. So, welcome everyone to my talk on Xenomai, building hard real-time systems with Xenomai. So for those of you who do not know me, my name is Jan Kiskar. I'm working at Siemens Technology, but today I'm standing here as a maintainer, or one of the key maintainer of this project. My daily work is dealing with embedded Linux for various devices in our company, and as such, I'm also maintaining a couple of open source projects, and Xenomai is among them. Yeah, and so today I would like to introduce you to Xenomai if you haven't heard about it, or give you a brief update where we are standing and also what people are doing with it. So, why still Xenomai? Some examples I've brought with me, a little bit look under the hood of it, how to set it up if you want to play around with it. Also look a bit into our community and the challenges comes with it, and give you a summary on that. So maybe if we talk about these days about what real-time and Linux, what would you associate with real-time and Linux these days? With real-time, you may have something in mind like, okay, it's some serious time-critical work that has to be done. And okay, if I want to do it with Linux, then I will use preempt.t. Natural choice. You probably will not think immediately about using Xenomai instead of that. And you would probably not associate, if you're thinking about real-time Linux and Xenomai, that you may have been in contact with it, hopefully not, at a doctor or at a hospital. That comes into the play, but you may also wonder why that Emmy is here. I will come to that later on as well. So first of all, why is preempt.t omnipresent, and how does it work in a nutshell? I mean, I'm not going to explain in all details how it works. This would be too complicated. But just to give you the idea, and the benefit of preempt.t is clearly that this enhances the existing kernel ABI to provide certain real-time paths through the kernel to the hardware and back. That's the great advantage. In theory, you don't have to touch your application, you don't have to touch your drivers, you don't have to touch, well, anything. At least this is one some people are dreaming of. In practice, in some cases, it actually works like this, by making the kernel itself way more preemptible than it is. It's always this trade-off between performance and determinism. Here we are with preempt.t really behind the determinism. Short reaction time, often deterministic reaction times, and for that preempt.t paves you the way towards the kernel. And obviously the other thing, which is a key asset of the preempt.t approach, it's going to be merged into the kernel next year. So maybe really next year this time. We are really looking forward with this. And that also obviously makes it quite present and quite easily accessible. That is not the case with the other solutions I will talk about. But yeah, that's the benefit of preempt.t. In contrast, there is another concept to achieve real-time with Linux, and that's the co-kernel approach. And Xenomai is implementing this approach. Xenomai is not the first one to implement it. There have been solutions around a long while ago, like RT-Linux, RT Core, RTI, and others. But Xenomai is the one, I would say, who survived them all and is now still standing and providing that solution. So what is the difference to preempt.t? So preempt.t was this unified, or is this unified approach to the kernel, while the co-kernel, as the name already suggests, there are two kernels. Well, actually, they're not complete separate kernels, but at least there are different schedulers, and there are different paths to the kernel for these different purposes. So the real-time tasks are handled by a real-time scheduler, which is separate from the standard Linux scheduler. And the underlying layer, in this case iPipe or Dovetail, we'll come to this later on, they basically enable you to receive also certain external events separately and before the rest of the Linux kernel, so you get a faster path directly to the real-time scheduler. Also, the real-time scheduler is at basically any time, not quite true in technical details, but in way easier as possible for the real-time scheduler to interrupt the Linux scheduler. So you have a different level of preemptibility here. How much it actually is in the end depends obviously on the hardware, but in concept-wise, preemption can be done at any point where there is no really critical synchronization points between the two. This is not a hypervisor approach, just to be clear. So we have a collaborative model here. The kernels or the code bases of the schedulers in the kernel are still in the same code base or in the same security domain. And also, this is the other thing, obviously, about that the application process using this real-time scheduler is not running on a different operating system. It's really the same application that you are spawning here can have real-time tasks and non-real-time tasks using these different schedulers while being one process. So the programming model is not identical to standard Linux application, but it's very close to it. Also the way how you debug these things and how you interact with these things. Now, the question is, why should I like to have this? And even at the time of PreemptRT and its omnipresence, there are three major reasons why people are still using co-kernels with Linux and are still taking the effort to maintain these differences. So one comes from the area of you may have an existing software stack coming from RTOS, coming from homegrown operating systems, which is not quite POSIX, well, because this is what Linux implements normally, which are quite slightly different. I mean, it can be sometimes just how exactly, how many priorities you have or how exactly the scheduler behaves in certain scenarios. And if this is not exactly mappable on a POSIX system, but your application stacks consisting of a few million lines of code actually relies on that, you may port it over, but it may also be hard to find the engineers who can still do that. And that's basically where the co-kernel comes into play by being able to modify the scheduler for that specific purposes without harming the standard use cases we like for Linux and all the negative impact it can bring on throughput and other aspects of the Linux scheduler. Also, the tunings there are different ways to tune these systems. Also, while still using the same tuning, the same performance-optimized tuning for your Linux part. So you can have different tunings for the different schedulers in the same system. While with Linux, you have to decide, okay, I want to be preempt none or I want to be preempt RT. I can't say I want to be preempt none on that core and preempt RT on the other, at least not up to date. You can also build additional APIs if needed, and simply model existing RTOSes. And this is what people did in the past as well and are still doing, and we are still doing even in some cases, just to make the porting of an application stack more handleable. Another reason to use that, this separate architecture, it first of all comes from the kernel perspective, it's quite some costs, but it comes with, for the user's space, also some advantages. So with PreemptRT, if you're using a PreemptRT application and libraries in between you, system calls, you don't know what, you're always kind of unsure, am I really now on this sweet spot path where PreemptRT can actually guarantee me certain reaction times? And that's not easy to find out, depending on the kernel version, depending on your external dependencies, libraries I mentioned, pulling in, maybe some of them actually randomly do malloc or something else in between. You never really know for sure. With the co-kernel approach and the separation you have, that brings architecturally some clearer paths between these two execution environments, and that can provide the application in way earlier a signal, you are leaving the known good path. And that's actually what Xenomike can provide to the application, saying, okay, once my critical application has been initialized with all the malloc and all the dynamics coming with initialization, I turn on, I'm now in operational mode, and if I'm leaving that mode, for example, by calling a system call of Linux, or by allocating memory, by touching memory, which is not yet ready for access, then I'm getting a signal. And I can early debug, so to say, my misbehaving real-time applications. So if you have complex application stacks, or you have to maintain them, also with developers who may have to change code paths while not being fully aware of real-time and real-time properties, that can be beneficial. And last but not least, some people tell us that there is actually some cases where this co-kernel approach still delivers better latencies. If that really matters, well, it depends obviously on your use case. If you're looking for 10 times better latencies, sorry, we can't. But if you are basically with your latency requirement on the edge, what PreemptIT currently can deliver, you may want to have some safety margin. Or actually it can lift you over the edge positively, and you get actually into an area where you can achieve things which are not yet achievable with PreemptIT. That specifically bites on lower end platforms. That specifically bites also when you are condensed, so you have to have the real-time workload and the non-real-time workload on the same core. This is where we see more significant difference in the latency with PreemptIT, even on more performant platform, than with the co-kernel approach. It can also help in some scenarios when you're scaling up, although there is some issue with at least with the legacy architecture of Xenomai as well regarding scaling. But we have also running systems where we reduced the real-time part to a number of cores, and the few other dozens of cores are doing non-real-time performance workload, and that happily lives side by side. So the other cores, the other dozens of cores, they don't have to bite the overhead that brings normally the high preemptibility with it. So, as I said, I'm working for a company who builds some stuff in this area. So I'd like to present you 2 use cases that we have for Xenomai. It's also the reason why I'm still doing that. At Siemens, we have, for example, the portfolio of motion control machines, or motion controllers for, well, drilling machines, and other things. And they have a quite demanding real-time requirements because, well, the faster the system are, the higher the accuracy is, the better the output is. So they're really after these lower latencies. They also have a system which is predating, not predating Linux, but close to, predating, but also predating PreemptIT and predating even Xenomai, and they cannot easily change this from one day to the other. So we are in a constant process of adjusting the APIs and reducing them to more and more POSIX, but still, specifically for the initial step to get the software stack over on a Linux platform, it was very helpful, and it still is very helpful to have flexibility in the API providing here. And last but not least, the colleagues are also quite after long-term support, as these machines or these devices live easily a decade or longer. Another use case, and this brings me back to my earlier slide, is from our Healthineers colleagues, Siemens Healthineers. So for quite a while, I think by now it's also about 15 years, they are running the data processing unit and control unit for these magnetic resonance imaging systems on Linux and on Xenomai. So not the whole thing is done with Xenomai, but there are critical parts. As you can imagine, the control of these measurements, when certain coils have to be stimulated in certain ways, when the measurement has to be collected, that is time sensitive. It's not immediately that the patient is in danger, but on the other hand, the patients usually are not for fun inside these machines, so the measurement really has to work reliably. So this is a critical operation. The software stack is quite complex, as you can imagine, and it's a mixture in the sense of having certain control elements, real-time elements, and a lot of data processing, number crunching, I would call it, to get this huge amount of data out of the measurements and in the end towards a terminal to visualize the results. So we have this co-location of a complex software stack, real-time, non-real-time, and the colleagues really enjoy that there is a clear separation between the both, and that not all developers have to be deep kernel experts in order to write applications which behave still properly on the real-time path, but they get the information early. And also we benefit from the fact that, as I said, the impact, the performance impact of the co-kernel approach on the non-real-time part is, at least the last time we measured, is still quite low. So that's our use cases, but there's way more outside. And that brings me to the Emmy, actually. So have you imagined that you watched a movie possibly recently which was shot by the help of Xenomai? So there's an interesting company which actually is doing motion control as well as we are doing, but for different purposes. Motion control in order to enable actors to interact with models of characters in the movie, which also enable them to interact or to act on platforms which are moving, or to interact also with virtual models which will be rendered later on for the final movie. So Concept Overdrive is providing this kind of solutions. So it's a mixture of standard components and obviously also specialized, customized solutions for the individual movies. They're doing it also for quite a while. Originally they did it on embedded controllers, later on RT Core, so these older real-time systems. And in the past years they have migrated over to Xenomai 3. And there's a very interesting talk I can only recommend by Steve Rosenblatt, CEO of this company, on last year's Xenomai meetup. Still online available. Watch it, and it's a mixture of interesting instructional technology as well as the connection to the movies. So be warned, the pictures I'm showing here, actually they are probably not taken with Xenomai yet, but there's a list he shared beforehand of recent movies that are now with the new architecture taken. And actually, that's maybe something to show one example. Whoop, where is it? No, not. Here is it. He just shared it 3 minutes before the talk, so thanks Steve, a lot. That's Dungeons and Dragons film recently shot, and that was taken with the new architecture. So yeah, maybe you've seen it on movies, that real-time is not about only industrial control or healthcare systems. It can be also like this. I really like this case a lot because it's a mixture of this application that we do as well with a complete different domain, way more interesting than our domain. Another use case, audio. So there's a Swedish company called Elk Audio. They're providing some kind of solutions and building blocks for doing low latency audio solutions. I think they also have a live jamming offering there. And one of the building blocks for them is an embedded Linux distribution called Elk OS, Elk Audio OS, which is tuned for low latency audio. So they support a number of these common embedded boards to build your own audio solutions. And they are now using Xenomai for quite a while, formerly 3, and now they actually have migrated us recently on the latest version. And that's a citation of them to achieve extremely low hard real-time performances. So they actually support both PREMTRT and Xenomai, but they say, okay, in most cases you might be fine with the standard PREMTRT, but it's really about this lowest latency real-time performance that gives you the best audio experience, then you have to go that path. So yeah, that's also a very interesting architecture and solution. It's actually, and if you go for the website, they have the code public on GitHub, so you can look it up and see how they actually integrate with Xenomai, how the application looks like, how they address these different operation modes as well. So if you're in music, I'm not, at least not at this level, you'll probably find also some interesting links how they achieve that. Okay, now let's have a look under the hood of this thing. So how do we build up the Xenomai stack? So the foundation for Xenomai is, first of all, a number of kernel patches, and this is common to the different Xenomai version we currently have in the field. It's called the dovetail patch that enables this split up of incoming interrupts and other events into these two domains, Linux or real-time. And that we maintain, so to say, as the must-have patch on top of a kernel. We support a number of LTS kernel with that, steadily moving forward. So currently there are 4 LTS kernel in the field. Probably this is something we have to adjust in the future regarding how many hands we have on that topic. Architecture-wise, we are on ARM, 32-bit, 64-bit, on an x86, obviously. And that's quite some interest, but still some way to go to get it on RISC-V, although at least some people are working on this. As I said, this is common for the most major version we currently have in the field.
and how it's being presented. So if you're dealing with maybe not just the plain vanilla LTS kernel, but if you have to struggle with a vendor kernel, we provide both a rebased patch queue, which allows you to more easily get that queue, hopefully, onto a vendor kernel, as well as a continuously merging branch, so that you can also see basically what's changing along the LTS updates. Just for reference, in the past, for the older kernel version, we had the IPI patch that still shows up, and as this also the adoption of these technology is sometimes a bit slower in that industry, you will probably still find a lot of references to IPI in the field. That is basically up to the 4.5, the 5.4 kernel, and it's only supported by Xenomai up to release 3.2. And we have also some older kernels here still in maintenance based on the civil infrastructure long-term kernel. So I already mentioned there are two major versions. So what are the major difference between them? The commodity we already discussed, the baseline kernel patch for Xenomai 3 series, and that's what probably most of the users currently are on. That consists, first of all, of another kernel change. This is an out-of-tree, think of a driver, out-of-tree kernel code base, the Cobalt core, the scheduler, plus its libraries. This is user space then. This core emulates a POSIX API natively as a ABI to user space. And on top, you then have either directly the POSIX library interface, so a second libc, so to say, for the scheduling relevant functions, or you may have on top further libraries in order to emulate some RTOSes or your own flavor of API. In that model, the core or the real-time drivers that we have in the core are, well, kind of forks or rewrites against a special API in the kernel, the real-time driver model. There are a couple of them, but don't expect to be as many as you have with the Linux kernel, obviously, because also a lot of the hardware is not really real-time capable by nature, so it doesn't make sense to write drivers for them. But still, this subset of drivers is limited. What users often then do, they come with their own driver source code in and implement it basically custom for their specific hardware they're designing. So the Xenomai 3 series, as I said, is currently various products, and that's also the reason why we currently have 3 stable series under maintenance, from 3.0 to 3.2. And that may also be reduced in the future based on feedback and based on our available capacity to maintain them, but currently it's quite easy for me, well, I'm the maintainer of this branch here, to handle the backports of the patches and to keep, hopefully, everyone happy with it. So that's for the Xenomai 3 path. Now there is even less, as it's called, EVL, Xenomai 4. That is driven by the former Xenomai maintainer, Philippe Jerome. So we basically handed over all the legacy stuff to me, and he was happy to drive this new activity with the goal to really reduce this co-kernel approach to its cores again. That comes with some price as well, because we are cutting off certain features. At the same time, it comes with the benefit of being, well, less, means ideally being faster, being more maintainable. So the EVL core, that's the pendant, so to say, to the Cobalt core, is differently maintained in the sense it comes with as a kernel patch pre-integrated. So you get the dovetail patches, and on top you get another branch which contains then the EVL scheduler patches in a kernel tree. So you don't have to deal with the integration. We will see it later on that you have on the Xenomai 3 side. It has an own ABI. It's separate. It's not POSIX. So there's also currently no foreseen path to emulate legacy RTOSes with this approach. Also, the drivers that are available, so for example, for the audio scenarios, they are actually in-kernel drivers enhanced by a separate out-of-band code path to enable the real-time code path. So you interact with a driver basically like you interact in the Linux with a driver, except that there is a special mode you can switch on that the event path and then the data path goes in via this co-kernel. That works quite well for some drivers. For others, well, you end up still having to rewrite certain things because simply the original kernel driver is not designed for real-time purposes. The goal of this approach regarding maintenance is currently 2 LTS kernels in flight, plus there's always a head of tree where Philippe is maintaining the latest version for the latest kernel. So that's the Xenomai 4 path. Now, brief look into if you want to try it out. So you see for Xenomai 3, you have to fetch basically two essential artifacts. The one is first of all Xenomai itself. So this project consisting of the libraries and the COBOL scheduler as a release or as the Git branch. Then you have to pick up the dovetail patches, and with this already the kernel. In the past, we had the kernel patches separately distributed. We no longer do this simply because there was not too much interest in that path, at least for most users we heard about. So it's just the kernel tree available. You have to check out the respective branch there that you want to have, which version. And then you have to marry these two elements, the kernel element coming from the Xenomai code base with the dovetail kernel. And that's done with the script here to basically run this kind of unification. It's kind of in-tree patching or integration of this. The advantage of this is that we can maintain mostly independent of the kernel version, the scheduler. We don't have to rebase it continuously over the kernel tree. The price is that the integration obviously is a little bit more tricky. Then you can compile the kernel, and next would be then going to the Xenomai code base, and there compiling the user space part, so the library there and the tools available there. So that's, in a nutshell, the from scratch approach if you do this on a distribution or if you do this for your embedded system in the build system there. For Xenomai 4, things look a bit different because of, as I said, all the kernel pieces come from one tree. So you can just clone here a different kernel tree, the EVL, Linux EVL tree, and you have all the needed kernel changes in one tree, configure and compile it, done. And then you fetch the library part, which also contains a few benchmark tools, just like the Xenomai above also contains benchmark and testing tools. And then you have the userland part. And those together basically makes your real-time system. Or if you do not like to write C anymore, there's also Rust binding by now available. It's not yet complete, but this is supposed to be done early next year. So if all of this is still too complicated, we also have a third option. That is currently only targeting the Xenomai 3, but this is going to be fixed in a couple of upcoming days. That basically builds you a ready-to-use mini Debian system with Xenomai pre-installed, with pre-configured all the tools and libraries you need. Basically, what you need is just to have a Docker running, in this case a privileged Docker locally, and you can just clone this repository and run the build instruction. Well, first of all, you can select basically what you want to build, which kernel configuration, which Xenomai configuration, and for which target you want to build. So all architectures are supported. As I said, currently only Xenomai 3. EVL is on the way, so it also will be covered soon. And we have a couple of, we have QEMU images, obviously, so if you really just want to try out how it feels, but don't look after latency, obviously, in QEMU. But we also have generic x86, BeagleBone Black for the ARM side, and the HiKey for the ARM64 side, and there will be more added in the future. It's not very hard to add further boards on that. Yeah, and it's also nice to have because it's you have the Debian system running then, and you can also then obviously play around and modify the system on the fly. And that's actually also the baseline. If you want a real bit a product out of this or a real integration, you can use this layer also as a baseline to then do your own customization on top. That tool is prepared for enabling that stacking. It's a little bit like similar like Yocto works in this regard as well, except that it pulls from the Debian distribution. So, talked about technology a lot, but there's more for an open source project, that's the community. And looking at the Xenomai project, I mean, it's been around actually for more than 20 years now, which is quite a long time. What also has been since then basically around are most of the challenges we are facing. So first of all, we have a user community, we know that. Sometimes we even know them personally, but that's where it stops because they cannot speak up. Even in 2023, it's still problematic for some companies to talk about what they're actually doing. It's also why I appreciate a lot these all open contributions of our users talking about their use cases. So we get also very little feedback in regarding how Xenomai is actually being used. What is relevant, what is no longer relevant, which version are you using mostly, which not. Up to the point that I actually tried to remove a subsystem, and only then, when the patch was about to be merged into mainline, the user spoke up and said, "Oh, but I'm using it." Okay, now, okay. So yeah, this is really a challenge for that community, given that the domain we are targeting, despite all these use cases I've shown, is comparably small. The other aspect is that as you can imagine, digging into the kernel, hooking all that up is not a beginner's task. So it can be quite problematic to adjust or to diagnose and adjust certain things in the kernel. So the number of these people who are really familiar within all the internals are few, while we need them to maintain the systems over all the time. On the other side, you see, again, we have been around for 20 years. The problem is solvable and has been resolved so far. No major outage on that side. And an also interesting aspect that I only learned the other years very recently is that we have an even larger community apparently in China right now, while the project originally comes from Europe. So how do you deal with that? So what we did in the past years is we try to improve the transparency of our workflow to make it more open for others to join the project and to contribute to that. That is the thing. If you don't get feedback, why should I work openly? There's always discussion. If I now invest into be more transparent, be more explicit, and no one really gives us feedback, why should I do that? But on the other hand, if you don't do that, you will never get feedback. So this is actually one of the investments we did in the past years. We also try to get more developers on board and really bound to the project. Well, for me on the company side, it was easier because I could more friendly ask my colleagues could you join the project? I have some tasks for you. Would you like to help here? And this is what happened. So we have more engineers on our side involved. We also like to see it from other companies as well. And just to be mentioned, in this case, Intel joined the project 3 years ago, basically bringing in also information. By the way, you know China is using this a lot. And they also granted some engineers on this topic, which is highly appreciated. What we do now these days, also again, initiative for Intel, we have a bi-weekly community call. You can just dial in. It's friendly it's not friendly to the US side, but it's friendly to the Asian folks because it's early in the morning of Germany, later in the evening of Japan and China. But anyway, it's open for everyone. You can join it and you can follow and ask questions this way if it's not on the mailing list or other channels. We had a virtual meetup last year, which initially was targeting a physical meetup, but for some reasons it wasn't still possible. Interesting outcome of this, the usual crowd, I would say, the usual amount of participation from Europe, from the Western world, and over 90% from China. The numbers were also quite impressive. So that was one of the reasons why we had this workshop just 2 weeks, last week actually, in Wuxi. Not hundreds of people, but at least we were about 50 from different corners, different companies, but that interest shows quite strongly. There have been companies representing application scenarios. There have been universities showing research on that, and it's quite impressive and quite interesting to see how the community is evolving there, so to say, not directly visible for us, and we try to engage with them. So to summarize, my summary is here, co-kernel is here to stay. As I said, we have been around for 20 years, and although there is the default choice, most likely for most of us, to use preempt.RT. Also for us at Siemens, we have more preempt.RT use cases than we have Xenoma use cases. The Xenoma use cases are not apparently going to go away. So they are valid use cases, I pointed out, so this is good to have this choice. There are different versions now of Xenoma, as I said. The project keeps evolving. It's not evolving like cloud technology. I guess this is probably also a good thing. The pace is slow but steady. But we're also committed to be really supporting these solutions for a very long time because this is what our users expect from us. So we're happy to take more active users. Stand up, provide feedback if you are using already, and if you will be using, also do that, please. We need them. Otherwise, we may make choices on the project side which are not in your favor, but then, yeah, you ask for it. With that, thank you for your attention, and I'm open to take questions.
So one of the things I think is missing for both Xenoma and preempt.RT, maybe I'm not aware of it, is published like benchmark numbers on your real-time latencies. So both projects have a marketing problem.
Yeah, that's the point. I mean, I've seen a lot of benchmark in the past 20 years, as long as I'm doing real-time Linux, and some of them are, they shouldn't have been published in this form. Others were helpful, others were more harmful because people were deciding based on 5% difference what technology to choose. When I'm in internal discussions about, okay, what real-time Linux do you recommend? I say, don't start with the benchmark numbers unless you can really explain to me you are so close to the limits. The problem with benchmarking is, as you know, it depends on where you're running it, how you're tuning it. If you stop when you have the numbers, or if you start to understand the numbers and try to dig deeper and make sure that you really benchmark correctly both sides. So just to give an example, I asked internally, please redo the benchmarks between XeroMi 3 and XeroMi 4. The numbers currently are not presentable, simply because it's not really in favor of XeroMi 4. But this is our fault. I've seen numbers from XeroMi 4 which were way better. Depends on, again, what mistakes you make along the line. And this is actually, although XeroMi is sometimes easier to configure, you can still make certain mistakes, or the hardware can make certain mistakes to ruin the whole benchmarking thing. I always recommend to everyone, if you have a case, benchmark your representative use case, not just the latency test like everyone is doing. So the representative I/O benchmark on your platform, and then come to a conclusion if the benchmark-wise makes a difference for you. There are other reasons, as I said, for using a co-kernel approach. If any of them applies, you may consider it. And if none of them complies, use PREMPT. My gosh, this is the standard.
So if I understand correctly, there are two schedulers. So does the application need to be aware of that to pass it on to the real-time scheduler than the normal one?
Yeah, to a certain degree. So that depends a bit on the version, and it's interesting also from our perspective. We still have to, I guess, look into that further. So with XeroMi 3, we have a mode where you link with a linker trick. You link against POSIX, and every thread that you create with real-time priorities are automatically handled by the real-time scheduler. Unless you explicitly, that again is when you put in something in the code, say, okay, but I want to be this on Linux only, even if it's real-time. So this is almost transparent. With EVL, you have a clear API separation. And if you look, for example, in that Elk Audio code base, you find there different code paths to create a real-time thread against the EVL API. So there are pros and cons between both. It's more explicit to have a separate API, but again, if you're porting over a large code base, or if you want to make a large code base compatible with both, there's a disadvantage. So my colleague actually asked me, if I now want to port over to XeroMi 4, I have to rewrite my application again, and you just promoted me to use POSIX, and now there is no POSIX. So there might be POSIX for EVL, for XeroMi 4 in the future. That's something we're currently considering. It's not impossible, but it's not the current default path, and nothing which is today available. Further questions? Okay. Otherwise, I'm still around. You can talk to me on this topic or other topics as you like. Thanks for your attention. Hope to see you.